All right, my friends, in this video, we're going to start working on our next project. Now, I'm really excited about this next project because it's a little bit different than anything else we've done in this course or anything else that we will do. So let's talk about what we're going to be building. All right, so we're going to be making a little maze game that is going to run directly inside the browser. So when a user starts up our application, we're going to show them a maze like the one you see right here. A user is then going to manipulate a little ball, like that blue one right there, to move it around the maze until it eventually gets to some target location, specifically this green square on the bottom left-hand corner. So a user is going to have to use the W, A, and D keys on their keyboard to move the ball around, like so, and then eventually touch that green square. And as soon as they do, they're going to win. So that's it. That's what we're going to be building. Now, this is not obviously a traditional web application. This is much more like a game. The thing I really want to focus in on this game that we're going to build is some of the data structures that we're going to use to actually generate the maze. Let's have a quick discussion and highlight some of the big challenges we're going to run into as we start working on this. Okay, so some of these are probably going to be pretty obvious when it comes to challenges of building this app. So the first big thing we're going to run into is how do we generate a maze at all? We're going to be building the maze from scratch. We're going to write the code to actually form that thing up. So we need to make sure that our maze has some valid solution. It also has to, have some level of difficulty to it. The next thing we're going to have to think about is how we're going to draw that maze on the screen. So are we going to use traditional HTML elements, or are we going to figure some other method or solution out? We also have to make sure that we can somehow get the keyboard keys to control that ball as well. So whenever a user presses W, A, S, or D on their keyboard, we're going to move the ball up, left, down, or right. And then finally, we need to somehow detect when the ball touches that green square on the bottom right corner. So for each of these challenges, let's talk about a solution very briefly. The first big issue is how do we generate a maze? Well, there are many different algorithms out there to use to generate a maze. We're going to use a pretty simple and straightforward algorithm to generate our maze, but we are still going to have to learn a little bit about a data structure called a tree. And we're going to also have to write out a little bit of code for recursion as well. So that's where we're going to kind of get pretty far down into the weeds and learn how to build the maze. To actually draw the maze on the screen, we're going to use a JavaScript library called Matter.js. Matter.js is used to draw or kind of simulate physical elements. So like a ball or a board or a spring or whatever else. It might be best to just take a look at the documentation for Matter.js. You can find it at this link right here. I'm going to open up a new tab right away and visit it. And once you go here, you're going to see several different physics demos right here on the main screen. You can also click on See All Demos. And if you, on this page, find the drop down at the top, you can select all the different demos they have available. So for example, I'll check out double pendulum, and there we go. About stack, there we go. And you'll notice that a lot of these, you can actually click and drag these elements around. So we're going to be using Matter.js, and we're going to learn a pretty good amount about it to actually implement the maze and all this other kind of stuff. Next up, how do we actually have the keyboard keys control the ball? Well, we're making use of Matter.js, and that this library has the ability to map some key presses to the movement of some shape or element on the screen, being drawn by this library. Finally, how do we detect whenever the ball touches the green square? Once again, Matter.js, it gives us the ability to detect collisions between different shapes or different objects inside of our app. So we should be able to write some code that's going to detect whenever the blue ball collides with the green square. And again, that's going to be essentially our win condition. Okay, so again, just a couple of big things for us to think about as we are starting this thing off. So let's take a quick pause right here. We'll come back to the next video. We're going to do a little bit of initial project setup and then immediately start writing some code to get a better idea of how Matter.js works. All right, let's do a little bit of project setup. I'm inside of a workspace directory of sorts. Inside of here, I'm going to make a new directory called maze. I'll then change into that directory and then start up my code editor inside there. Our project setup is going to involve a simple HTML file and a JavaScript file, which is where we're going to write all of our application code. So inside this new project directory, I'll first make a new file called index.html, and I'll throw a little bit of boilerplate in there. So I'll get my HTML tag, I'll get a head and a body, and then a script tag with a source of index.js, like so. I'm also going to add in a script tag inside the head element. We're going to use this additional script tag to get access to the Matter.js library. So I need to make sure that I provide a source right here to the Matter.js library. To get that, I'm going to go back over to my browser. I'm going to navigate to cdnjs.com. And then once here, I'll search for simply Matter. And I should see Matter-js as one of the first results. So there's a link to the library, so I can highlight that and copy it, and then put it into this script tag right here. Okay, let's also make sure we create the index.js file. So I'll do a quick console log and say hi there once again, as usual, just to make sure that everything is linked up correctly. So that should be it. Now we can go ahead and open up that index.html file inside of our browser. So I'll go back over to my browser, open up the HTML file, check my console, and just make sure that the console log that I added to the index.html file, which means index.js file, is there. Yep, definitely looks like it is. Okay, so that's all the setup we have to do, believe it or not. Yep, not a lot of stuff going on in that regard. So let's take a quick pause right here. When we come back in the next video, we're going to start to discuss the Matter.js library. We're going to write out a pretty quick example over the next couple of videos to get a better idea of how it works, and then we'll start to focus on building this maze. Now that we have done a little bit of project setup, I want to give you some high-level notes on the Matter.js library. Just so you know, Matter.js has some really good documentation, and you can always read it by going to the main page, brm.io/matter-js, and then finding documentation on the left-hand side. On the left here, you're going to see all the different objects inside of this library. I'm going to tell you about all the different objects you need to be aware of, but if you get stuck at any point in time throughout this application, you can always come and check out the documentation to get a better idea of exactly what we're working with inside this library. I want to give you a couple of highlights of the different things we're going to be working with in here. In general, this is just going to be some terminology so that you understand some of the code that we're going to be writing very soon. Okay, so here's some of the important pieces of terminology that you need to be aware of. The first piece of terminology that is used inside the Matter.js library is world. This is an object that contains all the different things or shapes inside of our application. So if we go back over to the official docs or the official page and take a look at all the demos and look at the mixed shape demo, you're going to see a bunch of different shapes all over the screen. The entire scene that we see right here is essentially represented inside of that world object. So this world thing that we're talking about right here, it tracks the location, position, speed, because see how these things can move, so the velocity of each item as well. They all get tracked inside that world object. The next piece of terminology we need to be aware of is engine. This is an object that has a bunch of different functions in it that's going to read in the current state of the world from the world object. So the world object knows where every shape is right now. It knows every shape's velocity, weight, and so on. The engine is going to read in all that data, and then it's going to calculate changes in positions for all those different shapes. So we can imagine that the world is kind of like a snapshot of everything as it stands in an instant in time. The engine is responsible for transitioning from one snapshot to another. The runner is what makes the world and engine work together. So the runner is going to essentially run about 60 times per second and tell the engine to process all the data stored inside the world object. The next big thing is the render object. So whenever the engine processes an update and says, okay, here's a new snapshot of data, here's a new version of the world, the render object is going to take a look at all those different shapes and it's going to show them all on the screen. So the render object is essentially what takes all of our data and shows it in this little element right here that we're playing around with. Finally, last piece of terminology is body. This is going to be a shape that gets displayed. There are many different types of bodies available to us when we're making use of Matter.js. So we can create a body that represents a circle or a rectangle or an oval or a triangle or just about anything else. Any kind of arbitrary shaped polygon can be created using the body object. So the application that we're going to create, the maze game, is going to have many of these different bodies inside of it. Now, one thing I want to mention here is that I'm going over this terminology rather quickly, because at the end of the day, you don't really need to understand the terminology here to write a Matter.js application. That's kind of the beauty of it. The only reason I'm telling you about these different pieces of terminology is that we're going to very quickly start to write some kind of boilerplate code to set our application up. And so I just want you to have some idea of what all these different terms mean for the purpose of writing that boilerplate code. But honestly, it's essentially write that code once to set up the application, and that's pretty much it. After that, the only things that we really need to be aware of is the body object, because the vast majority of code that we're going to write inside of our application is all about showing different bodies on the screen, essentially the different walls of our maze, and the ball that the user is going to be manipulating, and this green square at the bottom. Every shape inside of this diagram right here will be represented inside of our app with a body. So again, we really just need to understand what a body is, and all those other pieces of terminology I'm just throwing out there so that you're vaguely aware that they exist. Okay, so now we've got a little bit of terminology put together. Let's take one more pause and we'll start writing some code in the next video. Now that we have a better idea of some of these different pieces of terminology, let's start to write some code. Rather than directly focusing on creating a maze like this right here, which will end up being rather complicated, we're going to instead do a little demo first, just to kind of get a handle on exactly what Matter.js is. So we are going to re-implement this demo that you see right here, where we essentially have a bunch of shapes all in a pile, and we can drag one around and move them all when they all get kind of collisions between each of them. So first we'll build this, then rebuild over to the maze type implementation. So let's get to it. I'm going to first go back over to my code editor, and inside my index.js file, I'm going to first get started by requiring in or getting access to a couple of different objects out of the Matter library. So I'm going to say const, I'm then going to do some destructuring, and I'm going to get access to engine, render, runner, world, and bodies. And that's all going to come from Matter, like so. So when we included the Matter script tag back inside of index.html, that added in a new global variable of Matter, and that is essentially the Matter.js library. So everything we're going to work with is contained inside that object. In order to create an engine, render, blah, blah, all this stuff, we're going to pull out some of these different objects and then work with them inside this file. Now you'll notice that a lot of these terms right here are the same ones that we just discussed in the last video. So we're going to use the engine to essentially transition from a current state of our entire world or all the shapes we have into some new state. The render is going to be used to draw this stuff onto the screen. The runner is going to coordinate updates between the engine and the world. And then I had said on that diagram, bodies is kind of a reference to the entire collection of all the different shapes we can create. Essentially the same thing we saw on the diagram. So a bodies object represents our ability to create circles, rectangles, squares, and so on. So then inside of here, we're going to write out some boilerplate code. Now once again, it's not strictly necessary for you to 100% understand all the lines we're about to write. I just want you to have some terminology so you understand some of the boilerplate, but at the end of the day, a lot of this stuff just gets duplicated between all the different Matter apps you might end up creating. The first thing we're going to do is create a new engine by saying engine.create. We're then going to get access to a world that got created along with that engine. So I'll say const world is coming from engine. So technically, when we create an engine, we get a world object along with it. And again, a world is kind of like a snapshot of all the different shapes that we have. After that, we'll then create our render object. So this is what is going to actually show some content on the screen. So I'll say const render is render.create. And we're going to pass it in options object. Inside of here, we're going to tell the render where we want to show our representation of everything inside of our HTML document. So I'm going to say element is document.body. So in other words, go and render the representation of the world inside of document.body. And this is a additive process. In other words, it's not going to destroy all the content that we already have inside of our body element. It's going to instead add in a new additional element to the body element. After that, we're going to specify what engine to use. And then we'll pass in also an options object. Inside the options object, I'm going to specify the height and width of our canvas element that's going to be used to display all this content. So I'm going to put in a width of 800 and a height of 600. So these are pixel values right here. So we're saying give me something that is 800 units wide and 600 elements tall. Then after that, we're going to tell our render element or our render object to start working and start to draw all the updates of our world onto the screen. So I'll say render.run. I'll pass in lowercase render. So that's the actual render object that we just created. And then I'll call runner.run with runner.create and engine. So again, the runner right here is what coordinates all these changes from state A to state B of our engine. So with just that, we should be able to save this and then go back over and see something appear on the screen. So I'm going to go back over to my browser, I'll refresh, and I see a big black box appear. So this is where we're going to eventually see all of our shapes appear over time. So now we can start to think about how we just add a very simple and plain shape. To add a simple shape to our world, down here I'm going to say const shape is bodies.rectangle. And I'm going to pass in a couple dimensions for this thing. We'll talk about exactly what these dimensions represent in just a moment. I'm going to put in here 200, 200, 50, 50, and then an options object. And inside that options object, I'll say is static is true, like so. Then after that, I'll call world.add. I'll pass in the world that we got just a little bit ago when we created our engine right there. And then as a second argument, I'll pass in the shape that I just created, like so. Okay, so we'll talk about what that code is doing in just a moment, but first let's save this, go back over, and we can see a shape appear inside of our element. So that's the basics of getting something to show up on the screen. But obviously we just wrote out a lot of code that's possibly really mysterious, so let's talk about what's going on here after a very quick break. In the last video, we wrote out a little bit of code to get a simple rectangle to show up on the screen. In this video, I want to go over some of the code that we wrote just a little bit more and clarify a couple points. Once we get this final clarification out of the way, we'll then start to work much more quickly on the application that we're trying to build. So back inside my index.js file, the first thing I want to point out is where we had created that render object. As I mentioned, we provide the element property, and this tells Matter.js where we want to show our essentially drawing of the world inside the DOM. If we open up our element inspector inside of our development tools, we can see that this representation of the world, or this drawing, is a type of HTML element called a canvas. A canvas element is, for lack of a better term, a canvas of sorts that we can use to draw any kind of arbitrary shape that we want. Usually, we might use some kind of third-party library like like Matter.js to work with canvas elements. We can work with canvas elements directly using some browser-based APIs, but they are just a little bit tedious. So usually, anytime we want to use a canvas, we will commonly make use of a third-party library like Matter.js or something similar. When we created the canvas, we assigned a height and width to it. So if we ever want to change the height or the width of that canvas element, we could easily modify it right here. So for example, I could decrease the width to 400, and if I save and refresh, now this thing is going to be half as wide. For the first half of this application, we're going to just show a canvas element of 800 by 600. But if we have our final product, like our actual maze, show up in just that 800 by 600 frame, then it's not going to be that great, because if some user tries to play our maze game on a really, really big monitor, the maze is going to appear to be really, really small to them. So we're going to eventually add in some code to make sure that our canvas element spans the entire width of the screen and the entire height as well. So it's going to play equally as well on a small screen as a large one. But we're going to worry about that later on. Okay, so back over here, just a couple more things I want to point out. Down at the bottom, we use that bodies object to create a new rectangle. When we created the rectangle, we assigned it to the variable shape and then had a second line of code to add it to the world object. Just creating a shape or creating a rectangle doesn't make it show up on the screen. So for example, if I comment out the world.add statement and then refresh, well, nothing appears whatsoever. So we can create as many shapes as we want, but they all have to eventually be added to our world object in order to get them to actually show up. I want to show you something kind of interesting around that world object as well. Several times as we are writing out this application, I would encourage you on your own to open up your console and print out the world variable. So this world variable is the same one that we have created back right here. Well, technically up here, but the same one we are referring to right here. So as I've mentioned, this world variable contains a representation of all the different shapes inside of our world. If we print out the world variable, we can then expand it and see that it has several different properties. One property in particular, well, let me refresh, sorry, really quick. I need to make sure the shape is visible. So once the shape is very visible, I'll look at world again, and then look at the bodies property. As soon as I do so, I'll see that there's a single object inside there. This is the object that represents this rectangle shape. It has a lot of different properties in it that describe its physical representation in the world. So for example, it has an angular velocity, which is how quickly this thing is rotating and which direction it is rotating as well. It also has some other properties, such as position. So that is the physical position in the world in x and y coordinates. And then it also has a velocity property that describes how quickly this thing is moving to the left or right or up and down. Okay, one or two more things here. When we created our rectangle, we passed in an options object of isStaticTrue. That means that we want to show the shape and we don't want it to ever move under any circumstance. If we remove that property and then save and refresh, we'll see that the shape then falls down to the bottom. And every time I refresh, it starts back at the same spot and falls again. So by default, gravity is enabled in our simulation. So gravity is going to take that shape and automatically accelerate it downwards. So it is the isStaticTrue property right here that's going to make the shape stay exactly where it is. So if I save again, now the shape stays right there. Last thing I want to mention is some of the different dimensions or values we are passing in when we are creating the rectangle. The first two numbers represent the position in the world to place this rectangle at. These dimensions are measured from the top left corner to the center of the square. Just to make sure that's really clear, the top left corner of our canvas element is the 0, 0 point of our entire world. Our x-axis, or the x direction, runs from left to right, and the y-axis goes up to down. So when we say place a shape or a rectangle at 200, 200, that means start right there on the top left corner, go over 200 units, and then down, go over 200 units and down 200 units. And that is where the center of our rectangle should be. We can verify that by trying to do the same kind of rectangle, but instead placing it at 0, 0. If we do so, then I would expect to see the rectangle, or the center of the rectangle, based on like right there. So we're just going to see the bottom right corner of the triangle, or the rectangle now. So if I now refresh, yep, sure enough, I just see the bottom right corner. So as you would probably guess, the other two numbers inside of here, the 50 and 50, are how wide we want the rectangle to be and how tall it should be. So I can change the width to 100, and now this thing is going to be significantly wider. And I can change the height to 200, and it'll be significantly taller. Okay, so that's pretty much it. That is some of the very basics of Matter.js. Essentially, once again, everything that we wrote down to about line 14 or so is all boilerplate code, and we're not going to really change that stuff very often. In order to get some more functionality inside of our app, we're going to be creating a variety of different shapes, or rectangles, or circles, or whatever else, and then adding them all to our world. That is the primary means that we get some level of functionality inside of our Matter app. And that's pretty much exactly what we're going to be doing for the vast majority of our maze application as we start to put it together. Okay, so now that we've got a better idea of what's going on, another quick pause, and we'll start writing some more code in the next video. Rather than start working on our maze application right away, I first want to try to recreate this demo very quickly. Making this demo is actually going to be easier than you might think, and it's going to just get us a little bit more familiar with Matter.js before we dive off the deep end and start worrying about maze generation and a bunch of different crazy topics. So in order to create this demo right here, we're going to create a variety of different shapes. We need to make sure that they can all be clicked on and dragged around with the mouse. We also need to make sure that we show 4 rectangles along the edges of the canvas as well. So I need one on top, one on the right, one on the bottom, and one on the left. The purpose of these different rectangles is to just keep our shapes from flying off to the outside world. If we go back over to our application right now, and we turn off the is static right there, so I'm going to comment it out, and then refresh, we saw that our shape can very easily just fall off the face of the earth. So in order to keep this thing on the screen, we just have to show some rectangles around the border to make sure that it doesn't fall off. Okay, so that's pretty much it. We're going to make sure that we can show a rectangle on the top, right, bottom, and left. So to do so, I'm going to go back over to my index.js file. I'm going to find where I'm creating a rectangle right now, and I'm going to delete it. And then I will replace that with a comment that says simply walls. As we start writing Matter.js code, we're going to be creating a variety of different shapes inside of our index.js file over and over again. And so it's usually very good practice to add in some comments to describe the bunch of shapes we're about to add right here. Because otherwise, it's going to be kind of challenging to remember exactly what code creates what shapes. So then I'm going to create an array called walls, like so. And inside of here, I'm going to create the 4 different rectangles that we need. I'm going to first start with the top rectangle. So I'll call bodies.rectangle. Remember that the first 2 arguments are the x and y coordinates of the center of the rectangle, and the third and fourth are the width and height of the rectangle. For this very first one, let's take a look at a diagram and just make sure that it's really clear what numbers we're going to put in here. Okay, so the rectangle you see right here represents our canvas. As we saw just a moment ago, our canvas is 800 units wide. The rectangle that we want to show is essentially going to be like this right here. Notice that the rectangle is not completely inside of our canvas, and that's totally okay. That is actually what is going on the demonstration back over here. We can see that this rectangle is actually only halfway on the screen, and that's evident because that little red line right there. The red line is essentially at the center point of the rectangle. So the rectangle doesn't have to be all the way on the canvas. It can be half on, half off. And that's what we're going to do as well, just to make our code a little bit easier to understand. So we need to first provide the xy coordinate of the center of this rectangle. So the center will be approximately right there or so. So that's going to be 400 units over, and it's going to be 0 units down. So a y of essentially 0. Then in total, this thing's going to be 800 units wide, and its height, well, the height doesn't really make a big difference. We just need to make sure that we have some kind of rectangle there. We might use a height of like 40 or so, but really it's totally up to us. We can have any height whatsoever so long as it has a defined height. It just can't be 0. Okay, so let's now take those values back over to our editor. So back over here, I'm going to do a 400, so that's 400 units over, 0 units down, 800 units wide, and 40 units tall. And then I'll put on the options object with is static is true. And then after that, I'm going to make sure that I add this walls array to my world. So just a second ago, we saw that we could call world.add with lowercase world, and then whatever our rectangle was, so like bodies.rectangle or whatever. So we can pass either a single shape in to the world.add method, or alternatively, we could pass in an array of shapes as well. And that's why I created this as a walls array. So I'm going to pass all these different walls that we're going to create in at once. So I'm going to save that, go back over, refresh, and now I can see the top wall on there. Okay, so that's a good start. So now we can repeat that same process for the 3 other walls as well. Let me just very quickly draw out what the next 2 or 3 are going to be. So for the next one, let me just do a little bit of erasing here just to make sure things are nice and crystal clear, easy to read. So we can do the bottom one next. So once again, this is going to be 400 units over. It's going to be now 600 units down because remember our overall canvas is 800 by 600. It will be 800 wide, and once again we can use 40 tall. So I'm going to call bodies.rectangle again. We're going to be 400 units over. This time we're going to be 600 units down. We're going to be 800 units wide and 40 tall. And then is static is true. So I'll once again save, refresh, and now I can see the bottom border. Okay, let's get through the last two here really quickly. So I think you get the idea now, but honestly, we're going to have to do all this dimensioning stuff so often for this application that it's kind of worth just putting in a little bit of time from the get-go to make sure that these different values are really clear. So let's now do our left barrier. So this one will be slightly different. So again, we are 800 by 600 overall. So we're now going to go down 300 units. We're going to go over 0. This thing is going to be 40 units wide now and 600 units tall. And then something very similar for the right-hand side. We're going to be 300 down. We're going to be 800 over, so 800 to the right. We'll have 600 tall and 40 wide. Okay, so let's do both of those. Bodies.rectangle. So we'll do the left-hand side first. So this one is going to be 0 over, 300 down, 40 wide, 600 tall. And then finally the right-hand side. So we'll do 800 over, 300 down, 40 wide, 600 tall. And I'll get the is static true as well. Okay, so let's save that. Hopefully I didn't make any mistakes. If I did, we'll do a little bit of troubleshooting very quickly. But I'll refresh, and okay, it actually all was correct. So I've got top, bottom, left, and right. So now, if we go back over once again, and I add in one last rectangle, like the same kind of plain rectangle that we had before, and this time, rather than assigning it to a variable, I'll just add it into the world directly. So I'll do a world.add with the world, bodies.rectangle, and this time I'll do 200, 200, 50, 50. Save this, refresh, and now our rectangle falls down, but it hits that other one and it just stops right there. Okay, so that's definitely a good start. So let's take a pause right here. When we come back in the next video, we're going to throw in a ton of other shapes, and then we'll make sure that we can drag them all around with our mouse. So quick pause, and I'll see you in just a minute. Now that we have these borders around the edge of the screen, I want to try to enable click and drag functionality on this single little square right there. So more or less the same behavior that we see over here when we click and drag on a shape. Adding in this click and drag functionality is really surprisingly easy to do. This is something that Matter.js wanted to make really easy to add to any project, so it's just a couple of lines of code to add in the ability to click and drag something to move it around. To get started, I'll find my index.js file. I'll go up to the top and find where we are pulling off some different properties from the Matter library. I'm going to pull off another property called mouse constraint. So we're going to use this object right here to set up something called, you guessed it, a mouse constraint. This essentially means that we're going to set up something to respond directly to mouse input. I'm going to go down right after our runner.run line, and I'm going to create the constraint and then add it to our world. So I will say world.add world, and I'm going to pass in as the second argument mouse constraint.create. As the first argument to that, I'll pass in my engine. And then as the second argument, I'll pass in an options object that's going to have a mouse property. And for that, I'll say mouse.create render.canvas. And I think I missed one other thing that we have to require into this file or destructure off of Matter. We need to make sure we grab mouse as well. So I'm going to go back up here and just make sure that I pull in the mouse object as well. Okay, so believe it or not, that is pretty much it right there. So I'm going to save this. I'm going to go back over. And now if I refresh, I can click and drag on that object and throw it around the screen. You'll notice that when I click and drag, I get that kind of green line. That's supposed to represent a spring, or essentially a force that we are trying to apply to this little square. So now all we have to do is start to add in a bunch of other shapes to this thing, and we'll have something very much like the demo that we saw back over here. So another quick pause, and let's try to add in a bunch more shapes in the next video. Last thing I want to do to replicate that little demo we were looking at over here is to just make sure that we can show a bunch of different shapes at the same time. And there's not really any magic to this, and that's why I want to show you how to do it in a little demo. When I say that there's no magic to it, I mean essentially we're going to do the same thing as what we did before. We're just going to create a bunch of different rectangles and add them into the world. That's it. So I'm going to find where we're creating that one single lone rectangle by itself right now. I'm going to get a little comment right above it that says something like random shapes. Again, just to remind myself of what this code right here is about to do. And then I'll set up a for loop around that statement. So I'll say for let I, starting at 0, I less than 20, I plus plus, and I'll throw that in there like so. Okay, so let's save this. This should create 20 rectangles all on the exact same spot with the same size. So if I go back over and refresh, we're going to see very quickly that they kind of like spread out. That's because Matter.js wants to allow all these shapes to just contact each other on the edges. When we create a bunch of different shapes on the exact same point, Matter.js freaks out and tries to distribute those all around the screen. And that's why we end up seeing them all kind of stack up like so. So a slightly better way to handle this would be to slightly randomize the starting positions of 200 and 200. In order to randomize those starting positions, we can multiply the starting position by the width and the height of the canvas overall. And that should give us some even distribution all around the screen. To make sure that I multiply by the width and the height correctly, I'm going to define the width and the height up here at the top as constants. So I'll say width is 800 and height is 600. So now down here at options, I can replace the numbers with just width and height. And because the keys and the values are the same, I can leave it just like that. And those will be expanded to width is width and height is height. You might be curious why we're pulling out these separate variables right here. Well, it's because I essentially want to refer to the height and width later on down the file. If we start to reproduce numbers like 600 and 800 down here on this line of code, it might be hard later on to figure out exactly why we are using the numbers 800 and 600. And so by defining a constant at the very top, that means that if we ever want to change these values, we can change them in one location, and that will make updates all throughout the file. This is a technique that we're going to use quite a bit when we start working on the maze version of this app in just a moment. So now we can use those two variables to do some random placement. So for the position on the x-axis, I'm going to say math.random times width. And then for the position on the y-axis, we'll do math.random times height. And I'll save just to get that all down to multi-lined like so. Okay, so that should now give us some random distribution about the entire canvas. So let's now save this, go back over, refresh, and there we go. That's a little bit closer to the demo we saw over here, where they all get kind of randomized. All right, so now the last thing that we need to do is to just try to create some different kinds of shapes instead of just squares. So for that, inside of our for loop, we can add in a little if statement. I'm going to create a random number. So again, math.random. Remember, when we call math.random, that's going to create a number between 0 and 1. I'm going to check to see if that is greater than 0.5. If it's greater than 0.5, then I'm going to go ahead and create a rectangle. Otherwise, I'm going to create a different shape altogether. So if we don't create a rectangle and we have a value less than 0.5, I'm going to instead try to create a circle. So I'll do another world.add. I'm going to add a shape to the world. And then as a second argument, I'll put in bodies.circle. The circle method right here is very similar in nature to rectangle. The first two arguments are going to be numbers that represent where we want to put the circle in the world, and we have to put in those two values as x, y coordinates. So we can use the same trick we used right above. So I'll say math.random times width and math.random times height. Then the third argument is a little bit different. The third argument is going to be the radius of the circle. So in this case, I'll do, how about a slightly larger circle than the rectangles we're adding right now? So I'll do a radius of, well, actually technically it'd be like, how about 35 or so. That's the radius, so the entire diameter, or like the full width of the circle, will be 75, which will be just a little bit larger than the rectangles we're adding in. Okay, so I'll save this as well, refresh, and there we go. Now if we want to, we can adjust the number of shapes we're adding in. So instead of the 20 right there, we could do like, say, 50. Just make sure that you don't add in too many shapes, because otherwise your browser is going to lock up due to the processing power from trying to figure out what to do with all these shapes. Okay, so I'd say that's pretty close to the demo we just saw. Now you will notice that the demo over here has those little lines. The lines are meant to indicate the orientation of each shape. We can easily add those in by just adding in another option or two. We won't worry about that just yet, but there is one other option I thought you might be curious about. Right now we are operating the entire canvas in what is called wireframe mode. In wireframe mode, that means that we just see the outline of each shape. But if we want to, we can go back up to where we create our render. Here it is right here. And to the options object, we can put in wireframe is false. So that means try to render a solid shape as opposed to just the outline. When we do a wireframe of false, excuse me, I think it's capital F. Let's try that. Nope, I'm totally wrong. Wireframes, that's what it is. Sorry, I was going off of memory here. Lowercase f, plural s, that's better. Okay, so when we set wireframes to false, we're going to get solid shapes, and the colors for them will be picked at random. There we go. So now you can even see that the bordering shapes, or the bordering rectangles, are solid as well. Personally, I like the wireframe just a little bit more, but when we eventually put the maze together, I think you're going to find that showing the maze with some solid shapes instead of wireframes just makes the maze look a little bit more interesting. Last thing I want to mention is that we can customize the color that is being used if we go to where each shape is being created. So let's say that for each circle, maybe we want them all to be the color red. We can find where we create the circle. So that's the bodies.circle right here. And then as the last argument, we can put in an options object. And inside there, we can add in a little render property. So this is going to customize how the circle gets rendered onto the screen. So inside of this new render object, we can add in fill style. And then that can be any valid CSS color. So it can be like a normal color, like red. It can be a hex value, and so on. I'll try out red really quickly. So I'll save, and now all the circles are red. Or I can do, say, green. And now I've got a bunch of green circles. All right, so that's pretty much it for the demo. We've seen basically, believe it or not, just about everything that you need to see to build out the maze. There's only one or two additional topics that we need to be aware of when it comes to Matter.js, that is, to actually build the maze out, and that's really just understanding how to control a single shape using the keyboard instead of the mouse. So we'll figure that out. Honestly, that's not the worst thing in the world at all. It's actually rather easy to add in the keyboard controls. So most of the stuff around the maze that we're going to be doing is just discussing the algorithm we're going to use to calculate the shape of the maze. All right, so let's take a pause right here. We'll come back in the next video and start working on our maze code. Well, we now understand the basics of Matter.js, so now we can start to think about how we're going to build this actual maze. In this video, I'm going to give you an overview of the algorithm that we're going to use to generate the maze itself, and then we'll start to write out the code for it. So let's talk about how we're going to generate the maze. So we're going to go through the algorithm that you see right here. I'm going to first give you a verbal description, and then we'll take a look at a series of diagrams to help you understand how this actually builds a maze out. So the first thing we're going to do is create a grid of cells. A cell essentially represents each space that a user can visit. If we go back to the original diagram over here, right here, this kind of rectangular space, like right there, that is one cell. And then right next to it, we've got another cell. And then right underneath that, another cell, and so on. So we're going to build out a 2D array, or a two-dimensional array, to represent this grid of cells. We're then going to pick a random starting cell inside there. And then, starting at that cell, we're going to build a randomly ordered list of all of its neighbors. For each neighbor that we find, we're going to say that if we've already kind of visited that cell, so to speak, and we'll discuss what it exactly means to visit a cell in just a moment, we're going to remove it from the randomly ordered list. Then for each remaining neighbor, we're going to move to that neighbor, and we're going to remove the wall between those two cells. And then we're going to repeat that process for that new neighbor. So we're going to go back there and repeat this process over and over and over again. Now, I really don't expect you to understand this algorithm just from these kind of text steps right here. So instead, let me show you a quick diagram and help you really understand what's going on here. Okay, so this represents a starting grid. This is going to be a 2D array that we're going to build out of some JavaScript code. So we're going to pick a random starting cell inside of here. We're then going to iterate it using the same steps that I just spoke about right here. And we're going to see how it eventually is going to build us a randomized maze. So let me get a different color really quickly. Okay, so out of our grid right here, we're going to first start off with a random cell. So in this case, I'm going to start off with a random cell of that one right there. We're then going to take a look at all of the cell's different neighbors. So in this case, I'm going to look above, to the left, to the right, and below. So the 4 possible neighbors I have are 1, 2, 3, and 4. So I'm then going to pick one of these neighbors at random to visit. So maybe in this case, I decide to go down. So I would go down to this cell right here. When I go down there, I'm going to remove the wall between those 2 cells. So I would delete this wall right here. Then at this new cell, I would now take a look at all of this one's new neighbors. So there's a neighbor above, a neighbor to the left, below, and to the right. Now in this case, I have already been to or kind of visited or processed the neighbor above. So in this case, I would drop the neighbor above from my list of possible cells that I could visit. So then maybe in this case, I would decide to go to the left. So I'm going to visit to the left, go over here. And then just like before, I'll delete the wall right there. And now this process is essentially just going to repeat itself over and over again. So right here, I've got 3 possible moves. In this case, I'll decide to go up. And again, this is totally random. So I'll go up to right there. I will remove the wall in between. I've now only got 2 possible moves. So either up or to the left, because I've already been below and to the right. So now maybe I go, how about to the left? Now I can go up or down. And only a couple more steps here because there's one kind of corner case I want to point out to you here really quickly. So now maybe I would decide to go up. Now I'd go up here. I've only got one possible direction now. So I'm going to imagine that I come over, and then maybe I come over again. I come over again, and now I've got a random decision to make once again. I can either go to the right over here or below right there. So I'm going to imagine that maybe randomly I go down, and then randomly I go down, one more randomly down. I know kind of crazy odds to go down that many times in a row, but let's just imagine for a second. And now here's where we start to get to a really interesting situation. Let's imagine I come over here and end up right here. So now in this scenario, as I am right here, I don't have any additional way to move. But there are still unvisited squares all the way over here on the right-hand side that I still need to visit. So if I ever get to a point where I have no possible moves whatsoever, then I would essentially backtrack. So I would go back until I find a cell that does have a valid neighbor to move to. So the first one, as I backtrack, that would have a valid move would be this one right here. So I would backtrack from here all the way to this cell right here. And then back at this cell, I would once again say, what are my valid neighbors? In this case, I can only possibly go to the right, so I would move over that way. And then repeat the process for all the rest of those squares. Now, as I drew out some of these steps here rather quickly, I didn't remove the walls, but just to be clear, I still would be removing the walls all along the way. So I would drop that one, right there, right there, right there, and so on all the way through. Now this drawing is getting a little bit messy here. And one other right there. It's getting a little bit messy here, so I'm going to delete some of the red lines. And if I do so, you're going to start to see how I actually do end up getting a real maze shape here. So I'm going to delete all those lines that I drew on. And you can really start to see the maze start to form out. So if I imagine I kept on going through this, maybe I went from this one here to the right, and then up, and then like something like this. And if I trace that out and removed all the appropriate walls, I really would start to see the entire maze start to form. So drop the walls for each one that I cross over. And there we go. There's my entire maze. So that's the general idea. Again, we're going to build out the grid. We're going to pick a random cell, look at the neighbors, walk to each neighbor. As soon as we do, we're going to drop the wall. If we ever get to a point where there are no valid moves, as we saw right there, we're going to backtrack until we find a cell that there is a valid move at. And then we'll repeat the process from that cell. So this is how we're going to generate the maze. It's going to make sure that we always end up with one valid path to every single square inside of our grid. So this is going to guarantee that if I have a starting position up here, as we said that our app was, and I want to get to the ending position down here at the bottom right-hand side, there will always be a valid route to get there. So that's the idea. That's how we're going to implement this. As you can imagine, some of the code for it is going to be a little bit challenging, but at the end of the day, as long as you remember back to this example right here, it will eventually make some sense. One thing that I highly recommend that you do as we start to write out all this code is get out a sheet of paper and try to sketch out a grid like this one right here. I'm going to continue to do a lot of drawings to help you understand every step along the way, but it's really no substitute for you getting out a piece of paper on your own and kind of drawing out or diagramming the maze creation process. Okay, so now that we understand the general idea or the general strategy, let's take a pause right here and talk some more specifics in the next video. Now that we understand the general algorithm, I want to give you a couple more details that's really going to flesh out how we're going to implement this in our version of building out this maze. So as I said just a moment ago, we're going to end up having a grid of sorts. And this grid is going to be a two-dimensional array. It's going to have some number of rows. In this case, it would have 3 rows because there's 1, 2, 3. And there would be 3 columns because 1, 2, and 3. Having the grid alone is not quite enough or not the most convenient way of writing out this algorithm, however. So we're going to introduce one other data structure, or really technically 2 other structures inside of here to kind of keep track of how we're going to actually generate this entire grid. So when we spoke about how we're going to build this thing out in the last video, I said several times, oh yeah, we're going to remove this wall between 2 different cells. So the real question here is, how are we going to track where there is a wall and where there is not a wall? Well, to keep track of where there are walls and not, we're going to add in 2 different pieces of terminology. We're going to say that if there is a wall between 2 different cells that are right next to each other on the same row, so this wall right here, we're going to call that wall a vertical wall. If there is ever a wall between 2 cells in a column, so like this one and this one right here, we're going to call this wall right here a horizontal. So there are 2 types of walls that we're going to be concerned with, vertical and horizontal. To keep track of where there are any walls, we're going to add in 2 additional arrays. These are also going to be 2-dimensional arrays that we're going to keep track of in addition to the grid one. So we're going to introduce another variable or another 2D array here called verticals. And that's going to keep track of wherever there is a vertical wall. And another one called, as you would probably guess, horizontals. And this is going to keep track of wherever there is a horizontal wall. Now you can just about guarantee 100% that you're going to get confused by the terminology verticals and horizontals several times as we are writing out this code. So please, right now, really commit it to memory that the verticals array is going to keep track of walls that go up and down, and the horizontals array is going to keep track of walls that go side to side, like so. Inside of both these arrays, like I said, they're going to be 2-dimensional, and they're going to contain a bunch of different Boolean values. Each of these Boolean values is going to be either true or false. A value of true means there is no wall. So a value of true inside of verticals or horizontals essentially can be interpreted as true, this is like an open space. False means that there is a wall. So now with this knowledge, we can start to take a look at some different sample mazes and get a sense of the different verticals and horizontals arrays that we would create to represent each one. So I'm going to do a little bit of erasing here. And now I want to imagine how we would build up the verticals array and the horizontals array if I start to make a couple changes to this little demo maze that I have right here. Sorry, give me just 1 minute to clean this thing up. There we go, that's better. Okay, so I want to imagine for a second how I would build out the horizontals array and the verticals one if I remove that, about that one right there, that, and then we'll drop just a few more like so. So this right here would represent a valid maze. So now I want to imagine how I would generate or what the different verticals and the horizontals arrays would look like. Let's first consider the horizontals. So again, this would be a two-dimensional array. So I'll put in my outer brackets like so. And then I'm going to have, and this is critical, two inner arrays that represent the two kind of lines of horizontal bars or walls that I can have. The first one is right here. That is one line of horizontal walls. There's the second one right there. So in this case, remember, false means there is a wall. True means there is no wall. So right here, there's a wall. So I would do false, and I'll split F for false, and then open, open. So true, true. Then down here, open, closed, open. So true, false, true. So that's how we get from having these different gaps into this horizontals array. So now we can repeat the same process and consider what this would look like for the verticals array. So again, let me delete some of this stuff on here very quickly. And there we go. That's about good enough right there. So now we can consider the verticals array. What would this look like? Well, once again, this is going to be a two-dimensional array. It's going to have two inner rows inside of it. The first row of verticals is going to represent this spacing right here. And there's the second row right there. Now I'm using the term row here because I'm talking about like this row and this row. I'm not talking about like that line because I would really call that a column. So I'm saying that like this space right here would be the first element, then that is the second element, third one, and so on. Okay, so now let's consider how we would fill out the verticals for this case. So we have open, closed, open. So that's true, false, true. And then over here, we once again have open, closed, open. So true, false, and true. Okay, so that is the general idea. Oops, I misspelled verticals, by the way. So that's the general idea of how we're going to keep track of these different walls. So we have 3 data structures in total. We've got the grid to track all the different actual cells that we have. So we have 9 cells. Then we have horizontals to keep track of the walls that run from left to right. So like along that line right there and that line right there. And then we have verticals to keep track of the different walls that go from top to bottom. So right there and right there. One of the most challenging things to understand about this is that the verticals, horizontals versus the grid array are going to have different dimensions. So notice that the grid array in this case would be a 3 by 3 because there are 3 columns and 3 rows. But the verticals are going to have some very different dimensions. The verticals are going to have 2 rows. So here's row 1, row 2, and 3 columns inside there. So 1, 2, 3 over. So a 2 by 3 versus a 3 by 3 for the grid. All right, so this is another one of those topics. We're done with all the diagrams. This is another one of those topics where obviously, as I'm telling you this stuff, it's probably really complicated and you might be sitting there thinking, what in the world is going on here? And by the way, Stephen, I can't read your handwriting. Totally fine, totally fine. We're gonna write out the code here, and as we write the code, I gotta tell you, the algorithm actually ends up being kind of clear about what is going on. So we're going to write out all of our code, and I really think that rather quickly you're going to get a good understanding of how this maze is really being put together. I can tell you right now from building this thing out several times and figuring out the best way to explain it, the hardest part to understand about this is the different dimensions between the grid array, or the array that keeps track of which cells we've actually visited, and the verticals and horizontals array. That is by far the biggest challenging thing. Just understanding that there are different dimensions for each one that we need to be aware of. To understand that, we're going to come back to drawings like this several times as we start to write out that code, and just make sure that every step along the way, it is really, really clear where all these different numbers are coming from. Okay, so that's pretty much it. Let's take a quick pause right here. When we come back to the next video, we're going to start to write out some code to create the grid array, the verticals array, and the horizontals array as well. So I'll see you in just a minute. In this video, we're going to start to refactor our index.js file and get it ready for a maze. So we've got some code inside of here right now for that quick little demo. I'm going to delete a lot of the code related to this demo. So if you want to, you can always make a copy or a backup of the index.js file as it is right now so that you still have access to the code for the demo. But I don't really need that code anymore, so I'm going to delete some of the stuff in here related to creating all those different shapes. So inside my index.js file, I'm going to first get started by finding where we created that mouse constraint right here. Remember, this is what allowed us to do some click and drag on each of those different shapes. Our maze program is not going to have any click and drag functionality, so I'm going to delete all that mouse-related stuff. I'll also go back up to the top and delete the 2D structures that we have for the mouse-related stuff, so mouse constraint and mouse. Next up, I'll go down to the very bottom where we create our random shapes. So I don't need any random shapes anymore, so I'm going to take everything from that comment down to the very bottom and delete it. All right, so now the last thing I want to change really quickly, one more refactor. If we go back up a little bit, you'll notice we've got the height and width right here. I'm going to change the width to be exactly equal to the height, so 600 by 600. The reason for this is that some of the logic around our maze actually ends up being a lot easier to write if we have a perfectly square maze, so as tall as it is wide. As soon as we start to get a rectangular maze, some of the math gets just slightly more complicated. So we're going to first build a version of our maze that works perfectly with it being square, and then we're going to eventually refactor it to be rectangular in nature as well. Ultimately, we're going to make sure that the maze spans the entire size of this window, so like from this top left corner down here to the bottom right. But for the first implementation, we're going to have it fixed as just 600 by 600. Now with the 600 by 600, that means we also have to update the placement of some of our different walls, because these walls currently rely upon a 800 by 600 canvas. So now we have to go through here and update some of these values. I want you to recall that one of the reasons I said that we would create the height and width variables up here is to just have the ability to change these numbers right here and have all the appropriate variables inside of our file update. So as we start to rewrite or update some of the numbers inside of here, rather than using fixed values like 400, 600, 800, I'm going to instead have these numbers be references back up to the height and width variables up at the top. So in other words, we're going to have our walls lay themselves out automatically based upon the overall dimensions of our canvas. So that means that we will only have to do this one more update, and then as we start to change these numbers later on, as we want to test out different shapes of mazes, all of our different walls will relay themselves out appropriately without us messing around with this code at all. So we're going to go through here and update each of these rectangles. We're going to have as few fixed constant numbers as possible. So let's get to it. The first rectangle we created represented the top rectangle. So that's this one up here at the very top edge. Remember, the first number represents the distance from the top left coordinate to the center of that rectangle. So that's essentially the width of our canvas divided by 2. Then the second number, or the second argument, represents how many units down from that top left corner. In this case, we are 0 units down. Then the third number was the total width of that rectangle, which would be the width of the canvas once again, and then the height of that rectangle. We're going to leave the 40s in here as 40s, but we might eventually extract them to be assigned by a variable as well. All the other numbers inside of here are going to be either zeros or a kind of function based upon our height and our width. So let's do these updates. Okay, so the first one right here, again, that's going to be our width divided by 2, because we're going to go from the top left halfway over to right there. So that's the entire width divided by 2. Then the second argument will continue to be 0 because we're going 0 units down. The entire width of that rectangle is going to be width. And then its height will just be 40. Like I said, we'll leave that as a constant value inside of here for now. The next rectangle is the one at the bottom of the edge. So bottom edge of the canvas, that right there. So in this case, we're going to once again go over width divided by 2 units, but we're going to go down height units. So the entire height of the canvas, we're going to go down the height of the canvas. So once again, go over to the right, width divided by 2, and I'll go down height units. The width will once again be width, and the height of the thing itself will be 40. Okay, so next one, the third rectangle that we created was the left-hand wall. So in this case, we are going to the right 0 units, so essentially staying in the same plane, but we're going down height divided by 2. So that's still going to be 0. We're going to have height divided by 2. The width of this thing is going to be 40, and the overall height of the shape itself will be height units. In other words, the entire height of the canvas. And then finally, we've got the right-hand rectangle as well. So with this one, we want to go over the entire width of the canvas. We want to go down width divided by 2, or excuse me, height divided by 2. That's better. And then the entire height of that rectangle will be height. So same height as the canvas itself. Okay, so let's save this. I'm going to go back over, I'm going to refresh, and there we go. So I've now got a square canvas. The walls are kind of hard to see here just because the color is not that distinct. So if I wanted to, I could disable wireframes mode. So I could, or excuse me, I could enable wireframes mode, so I can set that to true, refresh, and now those walls are a little bit easier to see. So as you can guess, the benefit to this approach is that we can now change height and width as much as we want. So for example, I could go back to 800 by 600, and the walls are going to adjust themselves automatically. I could go to 1200 by 600. I could go to 1200 by, I don't know, 5, or how about 100, whatever. Doesn't matter. At the end of the day, the walls are going to lay themselves out appropriately. We're going to try to write out code like this as much as possible because, again, later on, as we decide to mess around with some of the different values inside of here, it's going to be a lot easier to change one number at the top as opposed to messing with a ton of code as we create all the different shapes. Okay, so this looks good. Let's take a pause right here and continue in the next video. In this video, we're going to start to implement those 3 different arrays we just discussed. We're going to first take care of the grid array. I want to first begin by giving you just a very quick reminder on what the grid array does, because there's a very particular way that we're going to initialize it. And if you don't really understand what the grid array does, well, a lot of the stuff that we're going to write here is not going to make a lot of sense. So we're going to have one array called grid, and this is going to be a 2-dimensional array. It'll be a 2D array, and every value inside of it is going to start off as false. The reason that we're going to start off as false, remember, the purpose of the grid array is to record whether or not we have visited each individual cell. So when we first initialize this thing, it's going to start off as a 2D array. If this is the maze that we are going to be building, then we're going to have 3 rows and 3 columns. So here are my 3 rows. I'm going to have 3 columns inside, and every element is going to start off as false. So I'm going to put in an F for each one. We're then going to pick a cell at random. So maybe the first cell that we pick is this one right here. We would now say that we have visited this cell because we have essentially done some processing work on it. Because we have visited this, we need to update our grid array. So I'm going to find the element inside the grid array that corresponds to that cell. So in this case, it would be that element right there. So I'm going to take that false, and I'm going to update it to be true instead. We can then imagine that we start to go through the algorithm. Remember, the primary step of the algorithm is to take a look at all the different neighbors. So that one, and that one, and then pick one at random and visit it. So let's imagine that I go off to the right like so, and I'm now at this cell. So I would now find the element inside of my grid array that corresponds to that cell. It is this one right here. So I would take that false, remove it, and update it to be true instead. Okay, so that's the purpose of the grid array. Let's just focus on creating this array first. So at the end of the day, what we really want is a 2-dimensional array that starts off with all false values inside of it. And for right now, we're going to imagine that we are building a maze that has 3 rows and 3 columns. So we're going to hard code those 3s in for right now, but we're going to update those to be a lot more flexible in just a moment. So to get started, I'm going to go back over to my code. I'm going to put a little comment header here that says maze generation, again, just to guide myself through this file. There's a couple of different ways that we can create this grid array. I'm going to first show you a very basic way, and then we'll refactor it into a little bit more fancy style. So a very basic way to do this would be to define a grid array and then iterate using a double nested for loop. So I could say for let I equals 0, I less than 3, I plus plus, And I'll set up another for loop inside there. So for let j equals 0, j less than 3, j plus plus. Then in the outer loop, I'm going to use this to push in each individual row. And then inside the inner loop, I'm going to process each of those rows and add in starting values of false. So I'll say grid at I dot push false, like so. So I'm then going to console log this. I'll save this, I'll go back over, and I'll do a quick test. So as soon as I reload, I can see the console log right here. I definitely have the correct structure to start off with. So I've got false, 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 and so on. So this is definitely one way to approach this. But anytime that we start using for loops like this, well, life gets a little bit challenging because now we've got all these different values and symbols floating around. As we've seen several times throughout this course, usually using a for loop, like the one we have right here, is not the best way of achieving just about anything. So we're going to instead use a little trick to initialize the grid array. At the end of the day, the code we're about to use is 100% equivalent to what we currently have, but it's going to be a lot more concise. So here's what we're going to do. I'm going to say that const grid is array of 3. So this means create an empty array that has 3 possible places in it. And when we create an array like this, we don't get some imaginary or we don't get some actual values initialized in there. So the array is told that it's going to have capacity for 3 elements, but right now there's no elements inside there. So if we were to run a for loop or a for of loop on this or a for each, it would not do anything at all. So we have to actually finish initializing this array by calling fill and then putting some default value inside there. So in this case, to initialize this thing, we can throw any old value in, and I'll show you why we can put any value in just a moment. Right now, I'm just going to put in null. So let me do a console log here, and you'll see what we get out of this. So I've now got null, 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 like so. So we now want to replace each of those null values with another array that has false values inside of it. So to do so, we're now going to map over this array. And for each element inside of here, we're going to return an array of length 3 that has values of false inside of it. So that's why it doesn't really matter what value we put inside of here to start. It doesn't matter that we throw in null because we're just going to replace it right away with a mapping statement. So I'll come back here, and I'm going to chain on a mapping statement. So I'm going to say for each element inside there, throw away the value of null. We don't care about that. Instead, return a brand new array that has 3 elements of false. So to do so, I'm going to use a very similar statement. I'll say create a new array that has length 3 and fill every value inside there with false, like so. Okay, so let's save this now. We'll go back over, and now you can see that we've got the exact structure that we're looking for. Now, you might be kind of curious, why do we have the map statement here as opposed to just like throwing in with a fill? Like, why can't we just put in false, 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 like so? Well, the reason is, in this case, we are creating one single array and then throwing it in at every location inside of grid. So in memory, there's only one inner array, and if we made a change to this inner array, it would affect every index. Well, let me show you that really quickly because it's actually a really neat little trick to do this. You would not expect it to happen. So here's our array. Those 3 inner arrays are the same exact arrays in memory. So if I do grid at 0 and I push in a value of true, and then I print out grid again, take a look at that. It added it to apparently each of these. Well, it didn't add it to each, it added it to just the one, but it's the same array in memory, so modifying one modifies all. So that's why we can't just do a direct fill like so. Instead, we have to do the map statement. And when we do the map statement, that's going to run the inner function 3 times, and each time we're going to generate a brand new and different array. All right, so we're going to be using this trick right here several times because at the end of the day, even though right now it might be kind of hard to read, it ends up being a lot easier in the long run to understand. And it also makes it a lot easier to come back and adjust the different values to change the size of the array. If we ever want to add more rows to our grid, then we're going to change that value of 3 right there. And if we ever want to add more columns, we'll change that 3 right there. So imagine for a second that we decide that we want to instead have a extra column on here, like so. So let's say that we want to have a rectangular maze. So we want that to be the starting point. To get something like that, we would come back here, we would change the inner arrays to length 4 instead. So now we've got 4 columns instead of the previous 3. So now I can save this, refresh, and now I can see 1, 2, 3, 4. So like I said, much more convenient way to create our nested arrays. All right, so that's it for the grid. We're going to take a pause right here, come back to the next video. We're going to tackle the verticals and horizontals arrays as well. So quick pause, and I'll see you in just a minute. In this video, we're going to generate our verticals array and our horizontals array. Once again, quick reminder on what both those do. So we have our verticals array and horizontals. The verticals array is going to keep track of every vertical wall we have. So those right there. Remember that these arrays are going to have some different dimensions than the grid array. So in this case, if we have a 3 by 3, the verticals, which only represents those labeled segments right there, is going to have 3 rows. So there's 1 row, there's row 2, and row 3. But in that side of there, it's going to have 2 columns. So to start off, it would have false, 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 and false. So then if we started off randomly right there and decided to move right there, we would find the corresponding entry inside of verticals that represents that wall segment. So that would be that one right there. We would take out that false and update it to true instead. So then horizontals is very similar in nature. Horizontals is going to keep track, let's change to green here, of all these horizontal segments. So likewise, it's also going to start off as a 2D array. It's going to have 2 rows, so row 1 and row 2. And then inside those 2 rows, it will have 3 columns. So we have false, 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 like so. So then we can imagine if we started off in this cell right here on the very bottom left-hand side, the matching element inside of our horizontals array is that right there. If we then go up, we would change that to true to say that there is now an opening right there, which would represent something like that, like so. Okay, so with this reminder, let's now go back over to our code. We're going to create verticals and horizontals. And again, the big thing we have to keep aware of or stay aware of here is that these are going to have slightly different dimensions than the grid array. Okay, so back over, I'm going to create my array of verticals. I'm going to create this array inside or with the same style that we used just a moment ago. So for verticals, I'm going to make an array. As we just discussed, this thing is going to have 3 rows inside of it. So the outer array is going to have length 3 because 1, 2, and 3. So back over here, I'm going to create an array with length 3. I'm then going to fill that up with null and then map over those values. And inside, I'll create a new array. And then here's where things get interesting. The inner array is going to have length 2. This array right here, 2 elements to it. So I'm going to make sure that I do a map, and I'm going to get an array with 2 elements inside, and I'm going to fill that thing up with a value of false, like so. So now I can repeat the same process for horizontals as well. So I'll do an array here. Once again, horizontals is only going to have 2 rows. So the outer array will have 2 elements to it. I'm going to fill that up with any old value because we're going to replace it in just a moment. I'm going to map. I'll do an array, and I bet you can guess what goes there. The inner arrays on horizontals has 1, 2, 3 elements. So I'm going to go back over. I'm going to make sure that this thing has 3 elements. I'm going to fill that thing up with false. All right, so let's now do a console log of verticals and just make sure we generated the thing correctly. So I'll flip back over, refresh. Okay, so I got verticals as the 3 rows, and it's got the 2 columns for each. So that maps up perfectly because we are representing that segment, all these like so. And then we can update our console log and instead do horizontals, save it, go back over, do the refresh, check this thing out. Okay, and this looks good as well. So we're looking at horizontals now. Remember, that's going to represent that, and that. And so we definitely want to have row 1, row 2, and each of those is going to have 3 false values inside of it. Okay, so it looks like we've generated all of our data successfully. Believe it or not, this right here, this is definitely the hardest part, without a doubt. Just understanding the purpose of these arrays. So now that we have this stuff together, the rest of the code we have to write is actually going to be kind of surprisingly easy, believe it or not. It's really not the worst thing in the world. There is one last change I want to make to this code, however. So quick pause, we're going to come back, and you'll notice we've got the value 3 and 2 inside of here all over the place. So we're just going to make sure that we abstract that out into a configuration variable, just like we did with height and width up here a little bit ago. So quick pause, and I'll see you in just a minute. At the end of the last video, I mentioned how we've got some hard-coded values inside of here of 3s and 2s. So the values that we currently have inside of here work perfectly for a 3x3 maze. Okay, I've really drawn the heck out of this thing, but you get the idea. It only works for a 3x3 maze. So if we ever wanted to have some different dimensions for our maze, well, we would have to go back through and start to update all these different values by hand. And I can just about guarantee you that we would make a typo somewhere and end up breaking our code. So I think that we should abstract out these different numbers into a configuration variable. So I'm going to go back up to the very top of the file, and I'm going to create a new variable that I'll call cells. I'm going to start this off as 3. Now, the value cells right here is talking about either the number of cells in the horizontal edge or the vertical edge. So for right now, we're going to imagine that the variable cells is talking about the number of cells either that way or that way. Because all of our mazes right now are going to be square, it doesn't really matter which dimension we're talking about. Again, we are going to eventually allow the creation of mazes that are not square, so like a 3x5. But for right now, everything we create will be square. So calling that variable cells for right now is more or less okay. But another engineer, if they looked at this, they might think that this is the total number of cells that we have. So the name isn't the best thing in the world. Whatever, we are going to change that in just a little bit as soon as we add support for rectangular mazes. So now we can use that variable to go back down and replace all the hard-coded numbers we have inside of here. So for example, I can find 3, change it to cells, change to cells, cells, and cells. And then the two values of 2, well, as you might guess, those are just going to be cells minus 1. So now you should not have any values of 2 or 3 inside of here at all. One good thing to test right now would be to try to change the value of cells and then console log out our grid, verticals, and horizontals, and just to make sure that they still make sense. So I'm going to try to increase the value of cells to 5 instead. I'll then go back down. I'm going to change the console log to take a look at the grid. So when I now console log the grid, I would expect to see a grid of 5x5. So 5 inner arrays, each of which have 5 elements inside them. So if I go back and refresh, yep, there's a 5x5 without a doubt. I can also do the same thing for verticals and refresh. Yep, that definitely looks correct. And I can do the same thing with horizontals. And I've got a 4x5. Also looks correct. Now, if you want to, this is a good spot to pull out your pen and paper and draw out what a 5x5 maze would actually look like. And then just make sure that we actually do have the correct dimensions on the verticals and the horizontals arrays. So I'm not going to flip back over and mangle my diagram anymore. I'll let you do that just in case you want to double check those values. But okay, I think overall this is looking good. So now we can start to write in some code after these arrays right here, where we're going to essentially walk through that grid, pick those random cells, and figure out exactly how we're going to remove all those walls from the verticals and horizontals arrays. So quick pause, and we'll start that up in the next video. Now that we have created those starting data arrays that are going to keep track of the state of our maze, we can start to implement our actual algorithm. So step 1 is to pick a random starting cell. To pick a random starting cell, we essentially need some starting dimensions or index that points into the grid array. So if this is our maze right here, we currently have 3 rows and 3 columns. So to pick a random starting cell, I need the index of some row and column inside of here. So that essentially means we just have to generate a value between 0 and 2. So maybe we start off with 0, and then we need another 0 and 2. So maybe we start off with 0 as well. So this would mean row 0 and column 0. So that would be right there. If we instead got something like a row of 2 and a column of 1, then we would go to row 2, which is right there, and column 1, which is right there. Remember, we're starting off at 0 here because we're using array index notation. And so with array index notation, we have 0, 1, and 2, and 0, 1, and 2. So to generate these numbers, we essentially just have to take a look at that cells variable that we just created. We're going to multiply it by a random number, and then we're going to take or round that number down to the lowest integer. So let's get to it. Back inside my editor, right after we create the horizontals array, I'm going to create a new variable called start row, and that's going to be math.floor of math.random times cells. And then I'm going to repeat that same calculation for my starting column as well. So now if we console logged out those variables of start row and start column, that's going to tell us exactly where we're going to start our iteration at. So as usual, quick test here, refresh, and we get 1 and 3. Now that's okay. If you recall, just a second ago, I had changed cells up here to 5. I'm going to take that back down to 3 really quickly just to stay in line with the diagram that I just showed you. So now if I save this again, now we are going to get some realistic values. So this would mean start iteration at 0, 0, 0, 2, 1, 0, and so on. We can keep refreshing, and it's going to show us these different starting points. Okay, so that's a good start. So now that we've got that starting point, I'm going to define a function that we're going to call over and over with this starting row and starting column. And inside that function, we're going to go through this algorithm where we're going to go through each of these steps that we just discussed right here. So I'm going to make a function called step through cell. That's a ridiculous name. If you think of a better name for it, feel free to do so. In my original notes for this, I called it recurse because we're going to eventually do some recursion. But honestly, call it whatever you want. Just make sure that it's kind of clear that this is going to be iterating through our maze or a collection of cells or whatever else. So when we call this function, we're going to pass in some row and column that we want to visit inside of our grid. So then right after step through cell, I'm going to make sure that I call it right away with start row and start column. So I'll do step through cell, and I'll pass in my start row and start column. So then inside of here is where we're going to start to put together all of our logic. I'm going to first begin by putting a couple of comments inside of here just to guide myself and make sure that I put down the correct sequence of steps. I'm going to generally be using this right here as a template for what I need to do inside of this function. So to get started, I'm going to first say if I have visited the cell at row column, then return. So remember, if we visited a cell already, then we should return early. We don't want to do anything if we've already visited this cell. So if we get past that little check right there, then we'll say mark this cell as being visited. Remember, to keep track of what cells we've visited, we have the grid array. So if we look at the grid at some index and we have a value of false, that means it has not been visited. So when we say that we want to mark this cell as visited, that means that we want to go into that grid array and update some element inside of it to true. That's what makes a cell be marked as visited. So then after that, we're going to assemble randomly ordered list of neighbors. Then for each neighbor, so I bet you can guess that we're going to do some iteration there. So for each neighbor, we're going to do a series of steps. First off, we're going to check to see if that neighbor is out of bounds. So at some point in time, with all this logic inside of here, we might end up trying to visit or be at a cell, say right here. And if we try to look at all the neighbors around us, well, obviously there's above and to the right, but we might also kind of accidentally write into our code that there is a cell below or to the left when, of course, there isn't one at all. So to handle the case in which we accidentally try to visit some cell that doesn't exist, well, we just need to make sure that we add in some code to check and make sure that we don't try to go in some direction that doesn't exist. So that's what this step right here is going to do. After that, we will check to see if we have visited that neighbor, continue to next neighbor. So we're going to end up with 2 checks to see if we have visited a cell. That's just a little bit defensive coding. We don't really have to add in 2 separate checks. This is just for our benefit in case we ever make a mistake. we can eventually remove one of the two checks if we really want to. So then after that, if we've gotten past these two checks, then we're going to go ahead and visit that next cell. So we're going to say visit that next cell. And of course, before that, we need to make sure that we remove a wall from either the horizontals array or the verticals array. And that depends upon whether we are moving to the left, right, up, or down. And then when we say right here, visit that next cell, that essentially means call our step through cell function again and pass in the row and column of the cell that we are now trying to visit. So that is it. That is the entire algorithm right there. That's pretty much all the steps. So we're really just going to come back through, and for each of these different comments, we're going to add in like 1 to 3 or 4 lines of code. So at the end of the day, like I said, the algorithm is really not the worst thing in the world, as long as you've got a sheet of paper that you can use to kind of diagram out what we're doing at each step. So now that we've got some guiding comments here, let's take a pause and start to fill in our implementation in the next video. Now that we have these guiding comments, we can start to put some implementation together. So to get started with the first comment right here, we want to check to see if we have visited the current cell specified at row and column. Remember, our grid array is what is keeping track of the different cells that we have visited. So we essentially want to look in that two-dimensional array, look at the appropriate element inside there, and see if it is true. If it is true, that means we have already visited the cell at row and column, and so that means that we'd want to return right away. So I will say if grid at row, so that's going to select our row, and column is equal to true, then return. Now, this is a funny little thing here. We are storing Boolean values inside the grid. So grid at row column is either going to be true or false. So we don't really need the comparison there, because if it's true, well, true is true. And so we are going to enter the if statement and return right away. So if we get past that check, then we will go ahead and mark the cell as being visited. So we just need to look at that same element inside of the grid and update its value to be true to indicate, hey, we've been here, we visited this cell. So I'm going to say grid at row and column is true. That's pretty much it for the first two steps. Let's immediately do some testing just so we can verify everything is working as expected. So I'm going to go down to the bottom. We're going to call step through cell one time with our random start and column, start row and start column. And then after that, I will console log out my grid. So because we are calling step through cell exactly one time right now, I would expect to find one element inside there that has been updated to true, and it should be random. So if I refresh the page several times, a different element should be getting set to true. So I'll go back over and refresh. I can expand the console log, and there we go. So one value inside of here has been set to true. I'll refresh again, and I now see a different element, and a different element set to true. So these are the starting locations of our iteration to build out the maze. So now that we have marked that as true, that means that we visited this cell. So the next thing we need to do is assemble a randomly ordered list of neighbors. So quick reminder on what that means. Let's imagine that we randomly select to visit that center cell on this grid on the first step. So we randomly select that right there. So we need to assemble a list of all the neighbors. So that's going to be above, to the right, below, and to the left. So 1, 2, 3, and 4. In other words, we need to determine the row and column indices of each of these pairs. So remember, our rows are on the left-hand side, so 0, 1, and 2. Those are the rows. The columns are up top, so 0, 1, and 2. So we need to say if we are at row 1, column 1, we need to select the cell right above at row 0, column 1. We also need to get the cell at 1, 0, the one at 1, 2, and the one at 2, 1. So this might seem like kind of a hard problem to figure out the different indices or these different neighbors, but in reality, it's actually really easy. Let me show you how. Right now, we know that we are at row 1, column 1. That is our starting cell. So we can actually figure out what all the different neighbors are by just doing a little bit of directed manipulation or some arithmetic on these starting values. The cell right above, so I'll say here, the cell above is always going to be at row -1 and the same column. We can actually check the math on this very quickly. So I'm at 1, 1 to start. If I want to go above to this cell right here, then I would take row minus 1. So 1 minus 1 is 0. That puts me on that row right there. And then the same column that I'm at previously, or at right now. So my column right now is 1. So row minus 1 and column is going to put me right here. And that's going to work for any value of starting row and column. Then if I want to go to the right and get the cell at the right, that's always going to be the same row as whatever I'm starting at, and column plus 1. So in other words, I'm going to take the same row of 1. I'm going to take the column I'm at right now, which is 1, add 1 to it, and I get 2. Then to get the cell below, there'll be row plus 1 and same column. And I think you can see where this is going. To get the cell to the left, it's always going to be the same row and column minus 1. So we really just have to add or subtract 1 to our different row and columns to get all of the neighboring cells. That's all we have to do. So now that we understand this, we can build out a list of all the different neighbors, or essentially the coordinates of each of them, by applying those rules. So right here on assemble randomly ordered list of neighbors, I'm going to say neighbors is an array, and I'm going to list out in row column notation the coordinates of the different neighbors around the current cell. So using the list we just went through, I'm going to first start off at we'll start at the top first. How about that? So I'll do the row minus 1 and whatever the current column is. Next to the right, we'll do our row and column plus 1. Then below is going to be row plus 1 and the same column. And then finally to the left is going to be the same row, but column minus 1. So those are the coordinate pairs of all of my different neighbors. So now the next thing we have to do is randomly sort this list. The randomly sorting part of this list is what's going to actually give us a randomized looking maze. Adding in the random sorting logic, or the kind of shuffling logic, is a little bit more complicated, so let's take a quick pause and tackle that in the next video. We now have our neighboring coordinate pairs right here, so now we need to take that list of coordinate pairs and randomize them. This is going to make sure that there's a strong randomization factor inside of our maze. If we always use this same order to visit our neighbors, then our maze is going to always look the exact same. So this is what is going to generate our randomness inside of our maze. Now, unfortunately, the JavaScript language does not have any functionality built into it to randomize the elements inside of an array. So we're going to have to write out a little function to do that for us. So I'm going to go up to the top of this section where I've got my maze generation comment. And inside of here, I'm going to define a new function called shuffle. So this is going to take some array and then randomly reorder all the elements inside of it. We're going to write out the code for this pretty quickly, and I'll explain what's going on along the way. So inside of shuffle, I'm going to first get the length of the array and assign it to a variable that I'll call counter. I'll then set up a while loop that I'm going to run until counter, or while counter, is greater than 0. Then inside the while loop, I'm going to get a random index inside of the array. So I'll say let index, or excuse me, const index is math.floor, math.random times counter. That's going to be a random index inside of the array. I'm then going to decrease my counter variable by 1, so counter minus minus. And then finally, I'm going to swap the elements that are at the array at element or at index of index and at the index of counter. So this is what is going to be the actual kind of swapping of elements to randomize the order. So I'll say const temp, short for temporary, is ARR at counter. I'll then update the value at index of counter to ARR at index, and I'll update the element at index to be whatever was previously at counter. And then finally at the bottom, I will return the array. So again, we're finding some random element inside there and swapping whatever that random index is with whatever is at counter. That will ensure that we swap each element at least one time. Okay, so let's go back down. to where we generate all of our neighbors. So right here, I'm going to wrap that function with shuffle and then do a console log right after it. Now to really test this out and make sure that we've got some correct values being generated and that they are in some random order, we should probably stick in some starting row and column to our function that we know is going to have some proper input, or excuse me, proper output. So we know that if we start at this 1, 1 index right here, we should see outputs of 0, 1, 1, 0, 1, 2, and 2, 1. So if we stick in 1, 1, those are the outputs we should get, but they should be in some randomized order. That's going to make this a lot easier to test than if we stick in the random start row and start column. So I'm going to update those two values to be 1 for just right now. I'm going to change it back in just a moment. I'm also going to remove the console log of grid just so we can read the console a little bit more easily without seeing a bunch of console logs start to stack up. All right, so I'll save this. I'm going to go back over and refresh. So here are the 4 coordinate pairs that are around 1, 1, and they should be in some randomized order. So let's see. I've got 1, 0. Let's check each of these off one by one. I know it'll be a little bit disorienting, but let's go through it. So 1, 0, that's the first one. We got that. Next is 0, 1, right there. Next is 2, 1, right there. And then finally 1, 2, right there. So we definitely have all 4. Well, that's fantastic. Now the only other thing we have to do is make sure that they get randomized each time. So I'll do another refresh. So I now see them in a very different order, and another different order, and another different order. So I'd say that we definitely have this kind of shuffling logic down pat. So this is looking pretty good. I'm going to remove that console log. We'll take a pause right here, and when we come back in the next video, we're going to make sure that we add in some logic to iterate through each of these different neighboring pairs and run some logic on each of them. So quick pause, and I'll see you in just a minute. The next thing we have to do is make sure that we iterate over each of these neighbor pairs. So I'm going to set up a for of loop to iterate through all these different neighbors. So I'll say for let neighbor of neighbors. I'm going to put the closing curly brace for the for loop right above this very last comment, like so. So then inside of here, we're going to do a couple of different checks. We first need to see if that neighbor is out of bounds. So remember, if we centered on the element like right here, we have definitely got all 4 sides covered inside of that neighbor's array. So we definitely do not want to go above or to the left at all. So to implement this, we can just add in a little bit of clever logic right here. First, right above, I'm going to get access to the neighbor variable. I'm going to pull a couple variables out of it using array destructuring. So I'm going to say next row and next column. And that's going to come from the neighbor variable. So next row and next column is essentially the cell that we are thinking about visiting next. So to do this check and see if that neighbor is out of bounds, I'll say if next row is less than 0 or next row is greater than or equal to cells. Remember, we defined cells at the very top up here. That's going to be the total number of cells in both the horizontal and vertical direction. So a check of greater than or equal to cells is going to handle the case in which we are trying to walk off to the far right-hand side or the far bottom edge as well. And we can also check to see if next column is less than 0 or next column is greater than or equal to cells as well. I'm going to zoom out for just a second so you can see that whole line very easily. So if we encounter this situation right here, and we do have a neighbor that is out of bounds that we're trying to visit, we still want to iterate through all the remaining neighbors, but we don't want to run any other code for this particular neighbor pair that we are looking at right now. So to do so, we'll use the continue keyword. Remember, the continue keyword means don't leave this for loop, just don't do anything else for the current iteration or the current step. So essentially skip over all the rest of the stuff in here and move on to the next neighbor pair. So then after that, this is going to be kind of a more challenging step. We need to check to see, or excuse me, this one's going to be easy. We need to see if we visited this neighbor, and if we have, we'll just continue to the next neighbor. So recall that inside of our grid array, we are storing all those booleans of true or false to record whether or not a certain cell has been visited. So all we have to do here is look at if grid at next row, next column is true, then continue as well. We could technically combine these two if statements together into one, but personally, I think that breaking them out separately just make sure it's really clear about exactly what's going on inside of our code. And anyone else who reads this in the future can look at this comment and just understand exactly what these two if statements are really looking for. Okay, now here's the part that's going to be a little bit more challenging. So now we need to take a look and decide if we are trying to go up or down, left or right. And depending upon that, we need to update either the verticals array or the horizontals array. So once again, let's imagine that we're at that center cell right here. So if we are going up or down, we are crossing over a horizontal element. And that means we need to update the horizontals array. Otherwise, if we are going left or right, we are crossing over a vertical element. And that means we need to update the verticals array. Now, unfortunately, with only the information that we have inside of this for loop right now, it's just a little bit challenging to decide if we are going up, down, left, or right. In order to really decide that, we could do some kind of comparison between next row and next column versus the row and column variables that we currently have. So we can essentially subtract each of these from each other and use that to determine which direction we are traveling. But there's a way easier way to do it than that. Remember the array right here of neighbors we put together? We said that row -1 was going to be above, and then the next one is going to be going down, and then the next one is going to be going to the right, or excuse me, did I get that in the wrong order? Sorry, that's going up, to the right, down, to the left. So in order to make that really clear and communicate that ordering down into our for loop, we can just throw on a third element to these arrays. And we can use that third element as kind of a flag to determine what direction we are traveling in down when we get to this statement down here. So as the third element in these arrays, I'm going to say a string right here of this one we are moving up, then right, then down, and then left. So then inside of our destructuring statement right there, where we're pulling out the next row and next column, we can also get the direction that we are traveling in. So we can use that variable right there to decide which way we're going and use that to decide if we're going to modify either horizontals or verticals. Now the rest of the logic we need for this step is just a little bit complicated, so let's take a quick pause right here and discuss exactly what has to be done in the next video. The last thing we have to do is to make sure that we remove the wall whenever we are traveling up, down, left, or right. So I want to first get a quick reminder by taking a look at a diagram at how we're going to update horizontals and verticals. Before I show you the diagram, however, or before we walk through it, I just want to remind you that inside this function, we have access to a couple of different variables. First, we have access to the row and column, that is the current row and column that we're working on. We also have access to the next row and next column, and that's where we are traveling to. So just keep specifically the row and column variables in your head for right now, because we're going to use those quite heavily in this last block of code that we write right here. Okay, so let's get to it. So what I want to focus on is how we're going to update the horizontals and the verticals array. We're going to first consider how we're going to update horizontals. So we're going to imagine that we're at this center cell right here, which means that our initial row is 1 and our initial column is 1 as well. And then we're going to imagine that we move only left or right. So only thinking about verticals right now. As a reminder, verticals are that, all these walls that I'm circling right now. So verticals in general is always going to be, remember, a two-dimensional array. It's always going to have 3 rows. So row 1, 2, and 3. So here's row 1, row 2, and 3. And then they all start off as false inside there. So this false right here corresponds to that element right there. This false corresponds to that right there, and so on. So what we really want to determine when we are deciding to go either left or right here from the center element is whether we are flipping that to true or that to true. That is the big question here. And we need to decide which of these to flip based upon the direction we are traveling and our current row and column. So let's figure out how to take the current row and column and the direction and translate it into some index that we can use to access the verticals array and update the appropriate element. Okay, so the actual row that we're going to update, that's actually pretty easy. The row that we're going to update inside the verticals array, let me put row right here, is always going to be whatever the current row is that we're looking at, because we're always staying inside of the same row. So row is never going to change when we update verticals or whenever we move left or right. However, the same is not true of column. So whenever we decide to move left or right, the column index that we want to update is going to be either 0 or 1. So either that element or that element. If we are moving to the left, then we want to update the element at column 0. That would be that one right there. So that's if we were going that way. We want to dump this element right here. So that means we need to access the verticals array at column 0 and update what is ever right there to a true. On the other hand, if we are moving to the right, then we want to update this thing right here and flip it from true to false. So that would be this element right here. So if we are going to the right, that means that we want to return an index of 1, because we want to get index of 1 and update this guy. So it's pretty clear here that when we are moving left or right, the row is always going to stay the same, but depending upon whether we are going left or right, we need to either access verticals at 0 or 1. That's all I'm trying to establish here. So now that we understand that, let's go back over to our editor and start to write out this logic. Okay, so I've got my statement right here. We want to remove a wall from either horizontals or verticals. So we're going to first think about moving left or right. So I'll say if direction, remember we've got the direction variable that we stuff into the neighbors array. If that is left, then I want to access verticals at the exact same row that we were working on. Because remember, the row doesn't change at all. It's only the column that changes. So if we're going to the left, we're going to look at columns minus 1. And it's minus 1 because remember, we start off with the column of 1. That's the column that we're at right now. So we're going to take 1 off to get 0. And then if we're going to set that to true, which means there is an opening here. Then we can handle the else if case. Otherwise, if direction is right, then we want to look at verticals again, still on the same row, but in this case, at the same exact column. We're going to update that to true. And I apologize, I typed in columns right here. That should be column singular, like so. Column in both cases. And that's pretty much it. So in both cases, we got the same exact row we're updating, but if we're going left, we're going to update at column minus 1. Otherwise, if we're going right, we're going to update at the current column to true. All right, so now it would really be nice to test this out. So to test this out, I'm going to go back up to where we established all of our neighbors. And I'm going to comment out the first 3 cases. So I'm going to say the only possibility here is that we can travel left. I'm then going to go back down and make sure that I'm still calling step through cell with a fixed value of 1 and 1. Then I'll save this, go back over to the browser, refresh. I'm going to print out the verticals variable. And now I can see that I've correctly updated that element, like this one right here. That one got updated to true. So that definitely worked out correctly, and that was for a move to the left. So now we can repeat that same process, but I'll comment out everything but a movement to the right. So now I'm going to only be able to move to the right, so I'll save this, refresh, print out verticals, and now I see right there, awesome, updated to true because I was moving to the right. And once again, that's because we wanted to update that one right there to true to represent an opening in that wall right there. Okay, so I think that we've got our verticals put together. So let's take a quick pause right here. We're then going to repeat the same exact process, but with our horizontals instead. So quick pause, and I'll see you in just a minute. All right, we've established how to update verticals. Now it's time to do the same thing for horizontals as well. So we're going to once again imagine that we're sitting right here in the middle, and we're going to go only either up or down. So we want to update either that or that right there. So let's think about the structure of horizontals again. So remember, horizontals has some very different dimensions. It's going to be a 2D array, but it's going to have only 2 rows inside of it and 3 columns because we are representing 1, 2, 3, and then row 2 is 1, 2, 3. So they all start off as false. So just to be really clear, that element right there corresponds with that wall, that element corresponds with that wall, and so on. So now if we think about moving up or down, once again, we're going to establish that we've got a starting row of 1 and a column equal to 1, and that represents the cell that we are currently in right here. So we need to figure out how we can essentially take these values and, depending on the direction, access and update either that element or that element. So once again, we can kind of ignore one of these variables. In this case, it's column. So whenever we move up or down, column is always going to stay the same. So we are going to update the element at column equal to whatever the current column is. However, the row variable is going to change depending upon the direction we are going. So if we are going up, then row needs to be whatever the current row is minus 1 to get that one right there. And then if we are going down, then row is going to be whatever the current row is to get this element right there, that wall, which is that right there. So in that case, it'd be row, which is, in other words, 1 in our case. So to get from the center element up, it's going to essentially be either row minus 1, and if we're going down, it's going to be whatever the current row is. And then column, either way, is going to stay the same. Okay, so now we understand that. Let's go back over and write out these else-if cases as well. So I'll say else if direction is up. Then we want to look at horizontals in this case. We want to look at row minus 1 and the same column, and we want to update that to true. And then else if direction is down, then we'll look at horizontals. I'm going to take whatever the current row is and the exact same column, and I'll set it to true. And that's pretty much it. Okay, so just like we did before, we're going to comment out a couple of the possible different directions and just do a quick test and make sure that everything is working correctly. So I'm going to comment out right, and we'll first try up right here. So again, if we are going to successfully go up, we want to update that element right there, which will be at index of row 0, column 1. Okay, so I'll save this. I'm going to go back over to the browser, refresh, print out horizontals. Here's my 2x3 array, and yep, I updated the correct value. So now we can test the same exact thing as well, going down. So I'll comment out up and uncomment down. So if we correctly update down, we should be updating that one right there to true. So I'll save, refresh, do horizontals again, and right there we've updated to true. Perfect. Okay, so that's it. I know this has probably been pretty nasty, but that is the hardest part of understanding this maze stuff. It is just understanding that depending upon the direction we are going, we have to adjust the indices of what wall we are trying to update. All right, so the last thing I'm going to do here is essentially restore my code to a working state. So I'm going to uncomment all these different directions. I'm going to make sure I get some commas back in there because my code formatter add-on automatically removed them. I'll then go back down to my step through cell call right here, and I'll throw in my start row and my start column. Okay, so the last thing we have to do is visit that next cell. So we'll take care of that in the next video. Now that we are forming up the verticals and horizontals arrays correctly, and we know we are because we've done a pretty good amount of testing, we can now move on to the next neighboring cell and essentially recurse through all of our different cells, calling step through cell each individual time. Remember the entire idea here of how we form the maze. We start off at some individual location, we then move on over here, and then we repeat the same process for this cell, going to all of its neighboring cells as well that we have not yet visited. So it is this recursion that's going to make sure that we walk through all the different cells of our little maze. Okay, so to do the iteration, or excuse me, the recursion, we'll go back down to the if statements we were just working on. Here they are right here. And right after the if statement, still inside the for loop, I'm going to call step through cell with next row and next column, like so. So now let's save this. We're going to go back over to the browser. I'm going to refresh, and then I'll print out verticals and horizontals. And now in both these arrays, we should see some number of values of both false and true. I'm going to take these false and true values, and I'm going to go over to our little diagram right here, and I'm going to manually erase some of the walls and see if it forms an actual maze like the one that we're trying to generate. Okay, so we have verticals of, I'm just going to write this down really quickly. True, false, false, true, and then horizontals of false, true, 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 false, true. Okay, so these are our verticals, and these are our horizontals. So again, this kind of value right here corresponds to that one right there. And for example, that true down there corresponds to that wall right there. So I'm going to go through and erase all the true walls. Because remember, true means that there is no wall available or no wall present. So first, we'll take our verticals. So I'm going to delete that one, and that one, and that one, and that one. So now the only verticals remaining are that and that. So I can repeat the same process for horizontals as well. So I've got on horizontals false, true, so that's open. True, so that is open. True, and true. And if we look at this pretty closely, we can see, yeah, without a doubt, we've got an actual maze here. So that's pretty much it. It looks like we have successfully formed up the vertical and horizontal arrays, and we can now generate a maze. Remember, one of the properties of our maze is that every single cell can be visited. Essentially, there are no portions of the maze that are completely blocked off or inaccessible. And this is what is going to allow us to make sure that we can always have a starting position for the ball that we're going to eventually show up there on the top left, and the completion on the very bottom right, like so. All right, so now that we are forming up the verticals and horizontals, we can start to take all this data and render it out onto our Matter.js canvas. So let's take one last quick pause right here. We'll come back to the next video, and we're going to start to take our grid, verticals and horizontals. We're going to iterate through all this stuff, and we're going to figure out where we want to draw some walls using Matter.js. So quick pause, and I'll see you in just a minute. Now that we have formed up our verticals and horizontals arrays, we need to take those two arrays and use them to figure out where to draw the different walls on our canvas using Matter.js. One thing I want to mention right away is that the different walls that we're going to show are going to be drawn using the rectangle shape that we've spoken about several times with Matter.js. So we're going to use a rectangle to represent each individual wall segment. So now we need to essentially just iterate over all of the verticals and all the horizontals. And for every false value that we find inside those two arrays, we need to draw a rectangle onto our canvas. Let's first start off with horizontals, and we're going to figure out how to iterate over that thing and then draw some number of rectangles using the data inside of it. So I'm going to go back down to the bottom of the file, and down here, I'm going to iterate over horizontals using a for each statement. Now I want you to recall that horizontals is a two-dimensional array. So when we do a for each on it, we're going to receive one of the inner arrays. I'm going to refer to that as a row. Then inside of here, I'll do a console log of row just to verify that that is going to be an array of Boolean values that represent where I want to draw some wall segments. So I'm going to save this. I'm going to flip back over, refresh, and there's the two console logs right there. So now we need to iterate over these two arrays, and wherever we find a false value, that means that we need to draw a wall segment onto our canvas. Remember, false means there is a wall, true means there is no wall. So to iterate through those inner arrays, we'll do a row.forEach, and I'm going to receive each Boolean value as an argument that I will call open. The idea here behind calling it open is that we're essentially saying whether this is an open segment of wall or not. So if open is true, it means that it is open. It's an open passageway, and we do not need to draw a wall segment. So then inside of my for each, the inner one, I'll say if open is true, then just return. So we don't want to draw anything in this case. Now, of course, we don't actually have to do a comparison with true right here because open is a Boolean already. So we can just take a look at open and say, hey, if open is true, then return. So otherwise, if open is false, then we do want to draw a wall segment. So I'm going to create a new variable called wall. And we're going to create this out of bodies.rectangle. So we need to now decide on exactly what arguments we're going to throw inside of there. What arguments we're going to pass to bodies.rectangle. Remember, the first two arguments are the x, y values to the center of this rectangle. And the third and fourth arguments are going to be the length, or the kind of width of the rectangle, and the height. So calculating those values out is actually going to be just a little bit challenging. So let's take a quick pause right here. When we come back in the next video, I'm going to show you a couple of different diagrams to help you understand how we're going to calculate those different dimensions. In this video, we're going to look at some different diagrams to understand how to calculate the different dimensions that we're going to pass into the rectangle function. So the first thing I want to do is go back up to the top of the file. All the way at the top, I just want to remind you very quickly that we've got a couple of different constant variables declared right here. We've got cells, which is the number of cells in either the horizontal or vertical direction. And then we've got a width and height. And very critically, right now, we are saying that the height and width are always going to be identical to each other. Eventually, we're going to allow these two values to vary to get a rectangular maze, but for right now, they are always going to be perfectly the same. So if we think about the combination of these two dimensions together, we can start to imagine that at the end of the day, every cell is going to be 200 units wide, because 600 divided by 3 is 200. So I'm going to define a little variable underneath here called unit length. Unit length is essentially saying that every cell that I create is going to be this many units tall and this many units wide. So to calculate the unit width, or the unit length, we would do a width divided by cells. And of course, we could do height instead. It really doesn't matter right now because, again, height and width are always going to be identical. So again, unit length is going to be the length of one side of one of our cells. So just keep that variable in mind for half a second. We're going to need to use that variable in order to figure out how to draw our individual walls. Okay, so I'm going to go over to a quick diagram and let's draw some stuff out here. So right now, we are iterating over our horizontals array. We know that that is going to be a 2D array. It's going to have the two different rows to represent that row and that row right there, each of those different wall segments. I'm going to throw some imaginary values in here. So I'm going to say maybe we've got true, false, true, false, true, false. So now if I wanted to reflect what actual walls we need to draw, I'm going to erase a couple elements here. So we would have no wall right there. We would have no wall right there. And then we would have no wall right there. So now, using that information, we need to somehow figure out how we can draw this rectangle, and this rectangle. We're going to first focus on how to draw the one at the top, this one right here. So we need to figure out how to go from our origin point, which remember is on the top left corner, that is our 0, 0. We need to first figure out how far over we need to go to get the center point of that rectangle. And then we also need to figure out how far down we need to go to get the center point as well in the vertical direction. So in other words, we need to figure out what that is right there. Okay, so when we think about the y dimension, so this off here to the left-hand side, we're essentially saying that we want to go down the height of one cell. So that is why we just created that unit length variable. To get the center point right there, we're going to first go down unit length. So in our case, that is going to be the, whatever it was it 200 pixels? So we'd be going down 200 units. That would be the center point right there on the vertical direction. Then the x direction to that center point, so this horizontal direction, would be 1, and a half cells over. So that would be unit length times 1.5. So that's how we're going to figure out how we get to the center point of that segment right there. But just doing like unit length times 1.5 isn't super useful, because if we start to think about how to show these other ones, like that segment or that segment, well, it's very clear that this is not just a function of the unit length, but it's also a function of what row these center points or these segments are occurring on, and what column as well. So in other words, as we start to think about how to get the center point of that next one down, it's going to actually be unit length times 2. So how do we kind of calculate that distance right there based on the unit length and what row it is on and what column it is on? Well, let me just show you the math, give you an idea of how this is all going to work out. In order to get the center point of all these horizontal segments, we need to get the column index that we are currently working on. So in this case, for the top one that we were just discussing, let me do some deletion here. So for the top element, this one again right here, we are operating on column index 0, 1, so 1 in this case, and we are operating on row index 0. So we need to do the column index times our unit length plus unit length divided by 2. So that's what is going to give us the x direction, or the x distance, like so. We can try to use this equation right here to figure out the x direction for each of these different segments. So for example, if we want to figure out the x direction distance for this one on the bottom left right here, that would be column index of 0. So we would do 0 plus 200, or excuse me, times 200. 0 times 200 plus 200 divided by 2, which equals 100. So that means that we would have 100 units over to get to the x direction center point. So then if we want to try to apply that formula again for this original one right here, that would be our column index, which in this case is 1, times 200 plus 200 divided by 2, and that gives us 300, which is definitely correct. And then finally for the last one down here, that would be a column index of 2 times 200 plus 200 over 2, and that would give us what, 500? Which is correct as well, because overall we've got 600, so we essentially want to go back 100 units, and that would be 500 to that center point right there, again in the x direction. Now that we've got that first little formula, let's try to write out that code back when we create our rectangle, and we'll think about the vertical direction after that. So on bodies.rectangle, the x coordinate here will be at column index times the unit length plus the unit length divided by 2. Now we don't have any variables inside of here called column index. So how do we figure out what kind of column we are currently iterating over and what row we are iterating over as well? Well, remember the second argument inside the for each functions. The first argument is the actual value where we are iterating over. The second argument is the index of that element. So for row right here, we would also have a second argument of row index, and that tells us what row we are currently operating on. And for the second one, we have the column index. That is what column we are currently iterating on. Now we can repeat the same process for the y direction as well. So I'm going to do a little bit of erasure. Okay. A little bit more. And I'm just going to draw in a couple more segments here by hand. There we go. So now we want to get that segment, and that segment. And now we're talking about this y direction. So how far down do we want to get this thing? Let's first think about this segment right here. So how do we get that segment based upon our row index, column index, and our unit length? Well, in this case, it is going to be our row index. So that is going to be like this direction or this row right here, which is our first row. So it's going to be our row index times the unit length. And then in this case, it's going to be plus the unit length. So let's try to plug in some numbers to get the y coordinate or the y direction to that center point right there. So I would do a row index of 1 times our unit length of 200 plus our unit length of 200. And that would be 400. So that means to draw out the y coordinate of this wall right here, it would be 400 units. Then if we think about this one right here, that would be a row index, in this case, of 0. So 0 times the unit length of 200 plus 200 gives us 200. So that means go down 200 units to get that one. And then this one right here is the same math as that one that we did just a moment ago. So that would be on row index of 1 times 200 plus 200 gives us 400 again. All right, so I know that this math is kind of nasty, but this is pretty much what has to be done. So hey, we got to talk about it one way or another. So now let's write out the equation for the y coordinate of this rectangle as well. So I'll put a comma in, and then we're going to get row index times the unit length plus the unit length. Okay, now that the third and fourth arguments, these are going to be way easier. So this is going to be how wide and how tall we want the rectangle to be. So in this case, we know that we want our wall to be like that long, like whatever the width of one cell is. That's how long we want it to be. And that is the direction in the x-axis. So that is going to be the third argument right here. We want that to be unit length, units long. So essentially the width of one cell, and that is what unit length represents. And then the fourth argument is going to be how tall we want the wall to be. So essentially, like, is it going to be really tall like that? Or is it going to be just very, very thin, like almost appearing to be a line? Well, we can just throw in some test value. I'm going to use like a fixed value of 10 here. So I'm going to say that my wall is going to be 10 units tall. All right, so finally, a last argument to the rectangle creation. We're going to make sure that we also mark this thing as static so that it doesn't kind of fly all around once we start to draw it on the screen. So I'll say is static is true. So now that we've created that wall, we can add it into our world. And to add in that shape, we will call world.add. We're going to add to the world object we had created earlier. And I want to add this wall. Okay, I know this has been some nasty math, but like I said, we had to go through it. So now that we've got that done, I'll save the file. I'm going to go back over and do a quick test. And I can see one wall appear right there. Now I can refresh this, and every time I'm going to see some walls appear in different locations to represent kind of like the randomness of the maze we are creating. Okay, so that's definitely working correctly, or at least I think it's working correctly. We won't know for sure until we also draw in the vertical segments as well. So I bet you could guess what's next. Let's take a quick pause right here. We're going to come back in the next video. We're going to add in some very similar looking code to handle the creation of all the vertical wall segments. And once we start to add that stuff in, then we will know that our maze for sure is working correctly. So quick pause, and we'll take care of verticals in the next video. Now that we've done all these calculations for the horizontals array, we can repeat that same process for verticals. So we're going to essentially do the same exact thing we did in the last video, but we'll do it way faster since we now understand essentially what we're trying to accomplish here. So underneath the horizontals for each, I'll add in a verticals for each. Then inside of here, once again, we're going to receive each row, and we'll get a row index. Then inside of here, we'll do a row for each. And on the row for each, we're going to receive the Boolean value, which we'll again refer to as open, and we get the column index that we are currently operating on as well. Then inside, we can say if open is true, then return right away. Otherwise, we want to create a wall segment. So once again, we'll do const wall is bodies.rectangle. So all we really have to figure out is the different arguments to pass to bodies.rectangle. This time around, the math is going to be just a little bit different because we are operating on a different direction. So let's once again go take a look at the diagram and figure out how to calculate the center point to the x and y coordinates for each wall segment in the vertical direction. Okay, so here we are again. I'm going to imagine some data for my verticals array. So in this case, I'm going to have 3 rows and 2 columns. And I'll remind you why in just a moment. So in this case, I'm going to throw in some imaginary data here. I'll do true and false, false and true and false. So we have the 3 rows in this case because we're talking about that set of wall segments, that set, and that set. So essentially this, 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 and this. And then we've got 2 columns because there's only 2 lines of those segments on here. So if we consider the different true and false values inside of this array, I'm going to erase wherever we have a true value. So we want that to be open, so no wall there. We want that to be open, no wall. And we want that to be open as well. So once again, let's imagine how we're going to calculate the x and y center points for each of these different segments. We'll first start with this one on the top right-hand side. And we essentially want to get the x and y coordinates of that x right there coming from our top left origin point at 0 and 0. So we need to determine that distance right there and that distance right there. This time around, I'm going to basically give you the formulas as opposed to trying to demonstrate exactly how they get calculated. It'll save us a lot of time. Essentially, it's the same thing as last video. We just need to calculate that center point right there as a function of the row and column that we are currently operating on and the unit length as well. So for the x direction, that x component right there, we're going to have our column index times the unit length plus the unit length. So let's try out the math for this. So in this case, we have a column index of 0, then 1. So our column index is 1 times 200, that is our unit length, plus 200, and that is 400. And that's definitely what this should be, because remember, we're essentially saying go over cell 1, cell 2, and then right there. So each cell is 200 units, so we get 200 and 200 over, and that takes us to right there. So 400, definitely correct. We can now repeat that for this next segment down here. That would be a column index of 0 times 200 plus 200 is 200. Yep, that definitely looks right to me. And then the last one down here on the bottom right is actually going to be identical to that first calculation. It'll be the 1 times 200 plus 200 equals 400. Okay, so that definitely solves this in the x direction. So now we get to repeat this same process, but in the vertical direction instead. So I'll do some erasing. I'm going to again try to find that segment right there. Well, let me just kind of redraw some of this stuff just so we can get some actual clarity in this diagram. Like so, and like so. So now we'll find the y component of that element right there. So just eyeballing this, it's essentially going to be, we're going down half the length of one cell. So I'm going to expect this to be about 100 units. So the formula for this will be our row index times the unit length plus unit length divided by 2. And then we can easily plug in some numbers to verify that that is the case. So right here, our row index is currently 0. I'll throw those on right now. So we get 0 times 200 plus 200 over 2, which gives us the 100 that I definitely expected. So then this one right here, we're talking about going half of one cell plus the full length of another cell. So again, just kind of guessing, I'm going to say it's probably supposed to be 300. Well, let's throw the numbers in. So now I have a row index of 1 times 200 plus 200 over 2. Yep, there's my 300. And then finally for this one right here, I have 2 full cell lengths plus half a cell length. So that will be hopefully around 500. In this case, my row index is 2, so I'll do 2 times 200 plus 200 over 2, And yep, that is the full 500. All right, so that's it. So we have to now add in that formula and the one we saw just a moment ago for the X and Y positions. So I'm going to go back over to my editor. We'll do a column index times unit length plus unit length. Then we'll do row index times unit length plus unit length divided by 2. And I got a little typo here that I'm going to fix. And then finally, we need to provide the width of a wall and the height of a wall. So remember, the third argument is going to be how wide the wall is in the X direction. So now we're talking about like if we have a really wide wall that looks like that right there, what is this X direction? So we'll once again use some like arbitrary kind of small number to give ourselves kind of a thin wall. And then the height of the wall, which is the fourth argument, is going to be a unit length. So that's going to be like a full 200. So as the third argument, I'll do a wall width of whatever we had before. Looks like it was 10. And the height is going to be the full unit length. And then finally, as the last argument, we'll throw on that same isStatic flag, like so. And then finally, underneath the wall, we'll do a world.add to our world object, and I want to add the wall we just created. Okay, so that's a lot of code. Let's save this once again, flip back over, refresh, and there we go. Here's our maze. So we can refresh a whole bunch and we'll see all the different mazes that we create. In every scenario, we should have like a solid continuous path. We should be able to visit every single cell and there should never be a blockage of any kind. And as I refresh a whole bunch, it definitely looks like that's the case. Now I know doing these formulas in the last two videos was really tedious, but the benefit to taking this approach is we've now got this kind of configurable calculation going on. There are very few static numbers inside of here besides the wall width, and we'll eventually abstract that out. So that means that in order to drastically change our maze, we can just manipulate these values right here. So for example, if I want to have a maze that is 5 cells wide and 5 cells tall, I can change cells to 5. And then everything else inside this file should automatically update appropriately. So now I can refresh, and now I've got 1 cell, 2 cell, 3 cell, 4 cell, 5, and same thing in the vertical direction as well. And we can start to really play around with that number a lot more, so I can go up to say 10 to make a much more detailed maze. There definitely is a limit to the number of cells you can have. Practically, I think that it's going to max out around 100 or so. If I do 100, okay, maybe slightly over 100. Since we're doing some recursion, we're going to eventually exceed the maximum call stack size, which means we are doing too much recursion. But you can see that once we have way too many cells, well, the maze is basically unusable anyways, so it's not really that big a difference. Let's try like cells 50. Okay, that's still a little bit too much. About 30. That's a little bit not quite usable, but we could very easily make it usable by adjusting our wall size. So that is the 10 right here in the horizontals and the 10 inside the verticals as well. So we can change those to like, how about 5? We'll do 5 right there and 5 right there. Save, refresh, and now it looks a little bit more like a maze than it did before. Okay, so this is great. We've basically got a proof of concept for our maze. I am going to take it back to cells of 3 because that's really nice for testing purposes. It looks like everything is pretty much working as we expect. So pretty much the last thing we have to add in here is the ball that the user is going to control. We need to add in the success area down here at the bottom right-hand side, and then make sure that we can control the ball with some keyboard controls. So quick pause right here, and we'll continue in the next video. In this video, we're going to focus on showing the goal on the very bottom right corner of our maze. The goal is always going to be exactly right here on the bottom right-hand corner, so this calculation is going to be pretty straightforward. We just have to be aware that we probably want to adjust the size of the goal based upon our unit length, or essentially the size of each individual cell. So in other words, if we have really large cells, as we do right now, we want to have a really large goal that fills up most of that space. But if we have some very small cells, like back just a second ago when I showed cells of 20 or 30, then in this case, we want the goal down here to be really, really small instead. So essentially, we just need the goal rectangle, or the rectangle that represents the goal, to be just about scaling itself with the size of our different cells. Okay, so I'm going to go back over. I'm going to go down to the very bottom. And down here, I'm going to create a new variable called goal. This is going to be a bodies.rectangle. And then right away, I'm not going to worry about the configuration just yet. Instead, I'll add in the code to add this thing to our world. So I'll say world.add world and goal. So let's think about how we're going to calculate the arguments for the rectangle. Remember, the first two arguments are going to be the x and y coordinates to the center of the goal. Okay, so quick diagram. So we're essentially saying that we just want to draw a rectangle like right here, and we need to find the coordinates to that point. So something like this right here. We can see how that lines up with the center. And about this right here, again, we can see how that kind of lines up with the center. So in this case, it's really not going to be that hard. We know that the overall width of this thing is our canvas width. So that's the overall width. And we know that the overall height is going to be height. So we want to essentially take the full width and the full height and then subtract the width of half of a cell. So that right there is 1/2 of a cell. And we are calling the variable that represents the cell dimension. Remember, we are calling that unit length. So essentially the center point to that rectangle is going to be our width of the overall canvas minus unit length divided by 2. And then the y component will be the overall height minus unit length divided by 2. And that's pretty much it. So let's take that information, go back over and add it in. So the x coordinate is going to be my width minus unit length divided by 2. And remember, this width variable right here is a reference back to the overall width of our canvas. Then my y will be the height minus unit length divided by 2. Once again, I made a typo right there on unit length, so I'm going to get that fixed up. All right, and that's pretty much it. So now we need to make sure that the size of this rectangle, so its height and width, which are the third and fourth arguments, also scale with the unit length. So you can imagine that if we always had a fixed height and width to the rectangle itself, as soon as we start to scale down the maze, as we have right here, well, the rectangle would be way too large inside of here. So to make sure that this thing scales, we can just do a unit length and then multiply that by 0.7 or something. So that means I want the rectangle size to just scale with the size of a cell. So I want the cell to essentially be 70% of the size of a cell. I could do unit length again times 0.7. And finally, I do want this thing to be static because I don't want it to move around. So I'll say is static is true. Okay, so I'll save this. I'm going to make sure that my cells variable back up at the top is back at 3. So we'll do a test with a very simple case to start. I'll go back over, refresh, and there's our goal. Now having the goal appear as this kind of outline, not that great. It's really not clear to a user what that is all about. We're essentially going to add in a fill to it as opposed to have it in wireframes mode. Once we add in a fill, we can make the thing green, and it will be a lot more obvious to our users that they're trying to navigate to that thing right there. Now that definitely looks good, but I want to point out a little issue. If we increase our cells right here to say 15 and save, then it looks like it's just about impossible to actually get to that goal because our bottom border is overlapping or kind of intersecting that actual goal that we're trying to get at. So I think that at this point, the borders that we have around the outside are way too thick. We need to probably reduce their size so that they're not going to actually interfere with the different elements of the maze itself. So for that, I'm going to go back to the section where we created all of our different walls. Remember, we put on that helpful comment just to help ourselves find this thing in the future. And I'm going to change the 40s inside of here, which represent the width of that wall. I'm going to change all 4 of them to, how about just 2, like so. That's basically really, really thin. And we can just about not see them, but now they're not really actually conflicting with any of the elements inside of our maze anymore. So I think that's definitely a better approach to take. Okay, so that's our goal. Now we do eventually have to add in some code to detect a collision between the ball that we're going to place and that thing to decide when the user wins, but we'll take care of that in just a little bit. For right now, let's take a pause, we'll come back, and we'll start to add in the ball that's going to start off at the top left corner. So quick pause, and I'll see you in just a minute. Now that we have our goal, let's make sure that we show a ball as well that the user can manipulate by pressing their keyboard keys. I'm going to find where we just added in the goal a moment ago. I'm going to add a comment right above it that says goal, just to remind myself that that is what that code is for. The variable name kind of explains that, but it's still good practice to have a comment anyways. So then underneath that section, I'll add in ball. So this is where we're going to draw our ball out. I'm going to first create a variable called ball. I'll do a bodies.circle, because in this case we want to create a circle, not a rectangle. Then inside of here, we could definitely have a fixed ball size, but once again, if we have a fixed ball size, it might make a lot of sense on how large the ball is when we have only 3 cells. But as we start to have a tighter and tighter maze, if the ball is too large, it's not going to actually be able to make it through the maze at all. So we probably just need to make sure that we kind of scale the size of the ball along with the unit length. The other thing we need to be aware of is that the first 2 arguments to circle is the XY coordinate of the very center of the circle. So we probably need to make sure that we also adjust that starting location to always be at the very center of that first cell right there. So let's get to it. For the starting XY coordinate, we're going to show the ball at unit length divided by 2. That essentially means take the width of this first cell, divide it by 2, and put it right there in the very center. And we're going to do that both for the X coordinate and Y coordinate as well. Then for the diameter of the ball, we'll do a unit length, so that's the width of one cell, and we'll make the ball half the size of a cell. So we can do a times 0.5 or divided by 2 as well. And then I can go ahead and add that ball into the world. So world.add, world, and ball. Okay, so I'll save this. I'll flip back over, refresh, and there we go. Now the ball is looking just a little bit too large. Well, I think I just made a mistake here. The third argument, I did this on my own when I was actually writing this application as well. The third argument I just assumed was the actual overall diameter. It's actually the radius of the ball. So right now, a unit length divided by 2 means that the ball is going to be essentially exactly equal to the width of a cell. Now, my mistake. So the last argument here, to be the radius correctly, it should actually be unit length divided by 4. So I'll try that again, refresh, and that's better. So now the ball is half the width of a cell. Okay, so now the last thing we really have to do is make sure that a ball can collide with the goal. And we need to make sure that when we press on our keyboard keys of W, A, S, and D, we apply some velocity or movement to the ball as well. So we'll first make sure that we can move the ball around. Let's take care of that in the next video. All right, let's make sure that when we press on the W, A, S, and D keys on our keyboard, we apply some movement or velocity to this ball right here. The first thing we have to do is figure out how we're going to detect whenever a user presses a key on their keyboard. Well, to be honest, there's not really a lot of magic to this. We're going to set up an event listener on our document. And that means whenever a user presses any key on their keyboard, anywhere on our application, we will be able to detect that key press. So underneath my ball, I'm going to add in a document.addEventListener. And we're going to listen for an event called key down. As you can probably guess, the key down event is going to be triggered anytime the user presses down on a key on their keyboard. So we'll then receive that event object. And I'm going to do a console log of the event because we're going to see something really interesting in there really quickly. Okay, so I'm going to save this, flip back over, refresh, and then I'm going to click anywhere on the screen inside my actual application and then just press a key. I'll first start off by pressing the key W. If I then expand this event object, we're going to see a couple of different interesting properties. So the one that is probably most relevant right there says key. So that tells us the key that was just pressed by the user. There's also a key code property as well. Traditionally, we use the key code property to decide exactly what character the user just typed on, as opposed to the key property. Each different key on your keyboard has a different code. So we can look up all these different codes to decide exactly what key was just pressed, and then impart some appropriate velocity on the ball in the appropriate direction. So I can also do an A. Oops, I need to select the actual app first. There's my A. That gives me a key code of 65. I can do a down, or excuse me, a S in this case. That represents the ball going down, 83. And then a D is a key code of 68. Now we don't really have to just click and press these different keys all day and look up the key code to figure out which key triggers which key code. We can always do a Google search. We can look up JavaScript key code. One of the first results here is keycode.info. This is a really great little site to figure out exactly what the key codes are for each key press. So if I do a W, it'll tell me, hey, that's 87. Left is 65, down 83, right is 68. So back inside of my editor, I'm going to remove the console log, and I'm going to instead set up a couple of if statements. So I'll say if event.keycode equals, and what's the first one we should do? Let's do up, which is a W. So if a user has a key code of 87, that means they want to go up. So inside of here, I'll say console.log, move ball up. And then I can repeat that same process for the other keys. So I'll duplicate that if statement down once, twice, 3 times. So that's up. I'll make this one a move to the right, down, and left. Then we can just update the key codes for those appropriate directions. So to move the ball right, I want to find my D key, so that's 68. So I'll update the 87 right there to 68. Going down would be 83. And going left would be 65. Okay, so let's save this. I'll go back over to my application. I'll refresh. And I can once again click inside of my application frame. And then I'll go up, right, down, and left. And I can definitely see that I'm doing the appropriate console logs for each of those different directions. Okay, so this is definitely good. Looks like we have a good start here. So quick pause right here. We'll come back in the next video, and we're going to figure out exactly how we can take these directions and actually translate them to adding some movement to our ball right there. So another quick pause, and I'll see you in just a minute. The last thing we have to do inside of our event listener is make sure that whenever a user presses on the appropriate key, we change the movement of the ball. So how are we going to do that? Well, essentially what we're going to do is take a look at the current velocity of the ball. When I use the word velocity, that means the speed in which the ball is moving. So we're going to take the velocity of the ball, and then we're going to update it or add in some additional velocity in the up, down, left, or right directions. To change the velocity of a shape, we have to get another object from the Matter.js library. So I'm going to go up to the very top of the file where we are currently destructuring a couple of properties. We're going to destructure another property called body, like so. This body object has some different functions on it that allow us to update the different properties inside of a shape. So we can use it to change the dimensions of a shape, its position, velocity, its rotation, and so on. So now that we've got that body object, let's go back down to our event handler. Down here, we're going to first take a look at our ball and get its current velocity. So I'm going to say const x and y with some curly braces because we are doing some destructuring here, ball.velocity. So x and y are going to be the current velocity of the ball. Let's do a quick console log and just see what those values are printed out as. Now I'll go back over, refresh, and I'll refresh once again. And right after I refresh, I'm going to press on the W key, which should trigger that code to go essentially right here, like go or print out the console log. So I'm going to refresh and then press a couple times, and we can see the console log of the x and y values. So we'll see the very first console log right here as the ball was falling down. We had an x coordinate or an x velocity of 0, which means that the ball was not moving side to side at all. But the y value was 8.23, which means the ball was going downwards, or it was moving downwards. Over time, once the ball kind of hit that block right there and started rolling slightly, we can see that these numbers got very, very small until now if I press again, they're at 0, 0 because the ball is not moving at all. Okay, so now that we've got these values, we can use those and add in some additional velocity to either the x or y coordinate. So I'm going to take care of moving the ball up first. I'll remove the console log and I'll say body.setVelocity. This is how we update the velocity of a shape. We'll say ball, and then I'm going to get the same x that we have right now. So I'll say x is x, and remember we can use that key value shortcut when those variables are identical to reduce it down to just x. And then my y is going to be whatever the y currently is -5. We are subtracting 5 here because we want to move the ball in the up direction. And to move it up, we want to have a negative velocity. So every single time that the user presses on the W key, which is key code 87, we're going to take whatever the current velocity is, we're going to subtract 5 to it, and set the velocity to that new Y velocity. Okay, so let's now save this and do a quick test. I'll flip back over, refresh. I'm going to refresh a couple times until I get a nice column like this right here, like lots of space to work with. I'll press W a couple times, and every single time I do, the ball moves slightly faster and faster, because every single time I press it, I'm accelerating I'm adding 5 units of velocity in the upwards direction. Okay, so that looks good. So let's now repeat the same process for each of our different directions. So I'm going to copy that set velocity, and we'll take care of going right next. So in this case, I'm going to clear out the X and Y inside of here. If I want to move right, I'm going to do X of whatever the current X velocity is, plus 5, and the same Y. And I'll delete that console log. Then to go down, I'll delete the console log. In this case, I still want to adjust the Y value, but to go downwards faster, I want to do a plus 5. And then to move to the left faster, I'm going to do same Y and an X of X minus 5. So again, to move to the left, we subtract from X. All right, so I'll save this. I'm going to flip back over once again, and now we should have full control of the ball. So I can go to the right, left, I can go up, and I can go down as well. And that's pretty much it. Now, if this thing feels laggy right now, that's totally fine. You can always try to close your developer console, and when you do so, you're going to see that the map or the maze is slightly more responsive and just a little bit less laggy. It's not a total solution, but definitely having your developer console open adds in a little bit more of a performance penalty. Now we can easily start to navigate through our maze. Okay, so this is looking pretty good, but I think that having the gravity turned on is a little bit distracting. So let's take a quick pause right here. When we come back to the next video, we're going to disable gravity inside of our maze, which is going to make controlling that ball just a little bit more easy. So quick pause, and I'll see you in just a minute. In this video, we're going to make sure that we disable gravity inside of our maze. Again, that's going to make this ball just a little bit easier to control. So to disable gravity, I'll go back over to my editor. I'm going to go to the very top, and I'm going to find where we create the engine right here. So in order to disable gravity, we're going to change a property on that engine variable. We'll say engine.world.gravity.y equals 0, like so. So that's going to disable gravity in the y direction entirely. So now if we go back over and refresh, the ball is just going to stay where it is until we start to apply some velocity to it. So I can tap on the button, and now I go to the left, right, up, down, and now it's a little bit easier to control than it was before. It's still kind of challenging to control because the ball starts to move like really quickly, but we'll start to address that over time. Eventually you're going to realize that having the ball kind of responsive is actually kind of nice when we have a really large maze and it takes up essentially the full width and height of our screen. So eventually we can add in some tweaks to make sure we don't accelerate the ball or set the velocity of the ball quite so high, but again, we'll take care of that in just a little bit. Okay, so this definitely works. So now the very last thing we really need to do to complete the entire game is to make sure that when the ball presses that completion block right there, we essentially end the game and say, hey, congratulations user, you just won. That's the last major feature we need to add in, so quick pause, take care of that in just a moment. The last big thing we have to add in to our application is to detect whenever our ball right here reaches the goal at the very bottom right-hand corner. So what we're really trying to do here, put in a more simplistic way or a more kind of engineering sense, is detect a collision event between two different shapes. Let's write out some code that will allow us to detect whenever two different shapes inside of our matter application collide with each other. So I'm going to go back over to my editor. At the very top, I'm going to find the matter object once again, and we're going to pull another object off of that thing called events. So this is an object that's going to let us listen for different things that actually occur inside of our world object. I'll then go back down to the very bottom of the file, and down here I'm going to add in a comment called win condition. So the meaning here is that, well, this is how a user can actually win our game or win the maze. So we're going to write out events.on engine. We're going to listen for an event called collision start. Double check your spelling on collision and make sure that you also have a capital S on there as well. Then the third argument is going to be a callback function that's going to be called with some event object. So this event object is going, or excuse me, this callback function is going to be invoked every single time that there is a collision between two different shapes inside of our world. For right now, I'll add in a console.log of event. Okay, so I'll save this, I'll flip back over, refresh, and we'll do a quick test. So I'm going to press the key and just make sure that my ball runs into some wall. That counts as a collision. So as soon as the ball runs into a wall, I should see a console log. And sure enough, I do right there. Now you're going to very quickly see some really strange behavior as we start to console log out this event object. The event object that is used by Matter.js gets reused between different events. So in other words, and this is kind of hard to internalize, but I'll show you some proof of it very quickly. This event object right here, there is one single event object that Matter.js owns. Every single time that an event occurs, it adds some properties to this event object to describe what just happened. It then sends that object into our callback function. Immediately after our callback function runs, all the different properties of that event object get wiped out and removed. That might sound really crazy, but let's take a look at the console log that we just got, and you're going to see that in action really quickly because of the weird behavior inside of our console. So notice how when I got the initial console log, like that right there, I see that pairs is an array of length 1. So that means that there is a single element inside of the pairs array. But if I expand this and look at pairs, it is now empty. And that is because when we got the initial console log, like right here, when we called console log on the event object, there was an element inside of that pairs array. But the way that the Chrome console works is that it doesn't really evaluate or look at these different properties too closely until you click on that little triangle and expand that thing. So when you expand that entry right there, Chrome takes another look at that same exact object. And when it takes that second look, it says, oh, well, it turns out there's actually nothing in pairs now, because Matter.js, after it called our event handler, wiped out all the different properties inside this object. So that's why we're going to very quickly see some really strange behavior from our console as we start to log out this thing. So let's take another look at how we can console log this thing out and start to get a real better sense of what's going on inside this event object without having to worry about the fact that all the properties inside of it get wiped out. So I'm going to remove the console log and replace it with event.pairs.forEach. So as we just saw, pairs is an array. So I'm going to try to iterate through that array. And I'm going to say for every collision, I want to console log that collision object. Okay, so let's try this again. If I flip back over, refresh, there we go, and get the ball to run into something again, now we're going to see a slightly different console log. So now we get to see what is actually inside of that pairs array, whereas before, by the time we looked at it inside of our console, it was already gone. It already got destroyed. So now we can see what is actually inside of that pairs array. We can see that it is some kind of object that has a lot of different properties that describes the collision that just occurred. The properties that you and I cared about the most is body A, right here, and body B. Those two properties describe the two shapes that just ran into each other. So we can see that I just had something with the label of circle body run into something with the label of rectangle body. And as you could probably guess, that means that the ball right here ran into one of the walls. So in order to detect whenever a user gets the ball right here to reach our win condition down at the bottom right-hand side, we need to just inspect the body A and body B properties. And if they are the ball and that little goal, that means that the user must have gotten to the goal and they must have won the game. All right, so let's write out some code to detect that kind of collision. I'm going to first go back over to my editor. I'm going to go up to the very top, and I'm going to change cells down to just 3. The reason for this is that I want to be able to very easily win the maze really quickly. So now this is a lot easier to win than what we had before. So now if I touch the goal right there, I can inspect this thing. I do get multiple console logs here because I accidentally ran into a wall. So I'm going to make sure that I select a console log that actually represents running into that body. There we go. That's one right there. So now I see that I've got a body A of rectangle body, and again, a body B of circle body. So these labels are not super helpful. So we need some different way to identify whether or not we just ran into the ball and the actual goal right there. So to make sure that we can easily identify when body A and body B are the ball and the goal, we can go back to where we create the ball and the goal, and we can add in a custom label to each of them. So I'm going to find where I create the ball right here. And then as a final argument to this thing, I'm going to add in an options object. And to it, I'm going to add in a label property of simply ball. I'll then find where I create the goal, right above. So here's the goal right here. And I'm going to add in a label of goal. So now whenever we see those console logs, we should have a more definitive label for both them. So I'll save this. I'm going to flip back over. I'm going to try to win again. There we go. Now if I inspect the console log, I get a label of goal and a label of ball. So that's way easier now to detect when we have the ball and the goal contact each other, as opposed to trying to figure out when, like, one was simply ball and the other was rectangle body, because every rectangle was going to be printed out as rectangle. So now back inside of our event handler, down here at the very bottom, we can just do a quick check and see if pair A and pair B are actually the ball and the goal. Now, if we start to write out an if statement here, we never really know if body A is going to be the ball or body A is going to be the goal, and vice versa for body B. So an easy way to kind of capture this and not have to write out a really long if statement right here to compare all different possibilities is to create a little array that I'll call labels. And I'm going to have inside there ball and goal. And then I'll say if labels includes collision dot body A dot label, and if labels includes collision body B dot label, then the user must have hit the goal. Let me save that so you can see that whole line. So inside of here, I'll do a console log of user1, like so. So again, if we tried to write out an if statement to just look if body A was ball or goal and body B was ball or goal, well, that would just be a really long if statement. So this is just an easy way to kind of collapse it down a little bit. Okay, so let's save this. I'll go back over, refresh, and now I can run into as many things as I want, and I don't see any console logs. It's only when I run into that goal right there that I see the console log of user1. So that's pretty much it. That's how a user is going to win the game. So let's take a pause right here. Now that we can detect this win, we can start to tell the user, hey, you won, or whatever else we want to do. So quick pause, and we'll take care of that in the next video. Now that we can detect a win condition, so whenever a user goes and hits that kind of completion area right there, it would be kind of fun to tell the user in an interesting way that they have won the game. So something a little bit more interesting than a console log. I've got an idea for kind of an interesting way of doing that. I think that when a user wins and they hit the ball against that kind of goal rectangle right there, let's try to turn gravity back on. And simultaneously, we'll also take all the different wall segments we have and remove the static flag from them. The net effect of both those changes is that essentially the entire maze is going to kind of fall apart and fall down to the very bottom, fall to like the bottom edge of the screen. So again, we're just doing this to make sure it's really clear to a user when they win a game. Okay, so let's give this a shot. The first thing we'll do is find the if statement we were just working on. I'm going to replace that console log right there. So inside of here, I'm going to turn gravity back on by writing out world.gravity.y equals 1. So that's going to accelerate all the different shapes we have down towards the bottom edge of the screen. The next thing I'm going to do is to loop over all the shapes inside of my world. I'm going to try to find all the different wall segments, so like these walls right here, and I'm going to remove the static flag from each of them. To make sure that we can easily find all the different wall segments, I'm going to go back up to where we create all of our walls, so the 2 for each loops. Here's one right here for verticals. I'm going to find the options object, and I'm going to add on a flag to it. I'm going to say label of wall. So as we saw just a second ago, we can use labels that are being applied to a shape that we create to easily figure out what type of shape it actually represents. So if I save this just for verticals right now, we can then go back over, refresh, and I can get a better idea of exactly what shapes are verticals by printing out world.bodies. So this is telling me that I have 10 different shapes inside the world. And if I look at the different label properties, label right there, I'll see that one has a label of wall. So that represents the one vertical piece that we have right there. So we can repeat that same label and throw it onto our horizontals as well. So I'll go back up to the horizontal section, and I'll add into that options object a label of wall. So now if we go back over again, refresh, print out world.bodies, we can see that we've got several different walls inside of here. The remaining rectangles are the actual kind of barriers or borders around the outside edge of our canvas. And of course, we have the goal and the ball as well. So now, whenever a user wins, we can iterate over world.bodies, and we can update the isStatic flag for each of the wall labels, or these wall objects, to false. And that's going to essentially allow gravity to affect all the different wall segments that will cause them to kind of collapse down to the bottom edge of the screen. So to actually write out the code for that, I'll go back over. I'm going to go back down to where we are computing our win condition. And after I update my gravity, I'm going to do a world.bodies.for each. And for each body that I am iterating over, I'll say if body.label is segment. So this is not a segment, but a wall. I had previously used the word segment, but figured wall made a little more sense, so we'll stick with that. And then to update the static property, we're going to once again use that body object that we spoke about just a little bit ago. I'm going to call the setStatic method on it. As you could guess, that's going to update the static flag on an object. So we're going to take the body, and we're going to update the static flag to false to say this thing is no longer static. So gravity and other forces can now affect it. So I'm going to save this, go back over, refresh, and now if I go ahead and win, everything kind of falls apart. So again, this is just kind of a fun little animation that a user can see once they actually win the maze. We will eventually put on a big message to the user that says, hey, you won, right on the very center of the screen, to make sure that it's just super clear that they won, but we'll add in one or two other features before we take care of that. So now for a really fun test, we can go and update the number of cells we have. So I might go to like 6 or so just to make my maze a little bit more complex. And now if I win, everything falls apart. And then the user can still kind of mess around and move all these different segments around. Okay, so this is looking pretty good. So the last really big thing that we have to accomplish inside this app is to make sure that it's not limited to this fixed size right here. At present, we've been saying many times that the height and width are always going to be identical. So if we start to change one of these values, like let's say I change the height to 800 and refresh, well, everything doesn't quite work as expected. So we're going to make sure that we can have rectangular mazes. We're going to, in particular, make sure that we can have a maze that fills up the entire screen. And so we're going to have to update several sections of code to accommodate for that. So let's take a quick pause right here and start that refactor in the next video. Well, now that we've got just about everything working as expected, let's start to think about how we're going to actually scale this entire game to fill up the entire screen. So I want to make sure that no matter what size browser window the user is using, I want this canvas to stretch from the very top left corner all the way down to the very bottom right. To do so, we're going to add in one CSS rule, and we're going to change a couple of different variables inside of our JavaScript file. And just about all the logic is going to remain the same. We just have to make sure that at several different locations, we respect a measurement in the Y direction and X direction as opposed to what's going on right now, where we just assume we always have an identical width and height no matter what. Okay, so first things first, what's with the CSS rule that I just mentioned? Well, if you open up your element inspector and take a look at the body element right now, you might notice that the body by default has a margin of 8 pixels on it. So that is preventing our canvas right here from getting truly to the top left corner of the browser window. So let's make sure that we can just remove that default margin on the body. To do so, I'll go back over to my editor. I'm going to open up the index.html file. Here it is right here. In the head element, I'll add in a style tag. And then inside there, I'll select the body and set margin to 0. That's going to remove that extra little bit of space around our canvas. If I now refresh, I should see the canvas go truly up to the top left corner. All right, so now how are we going to make sure that this canvas fills up the entire screen? So from that corner down to the bottom right. Well, if you take a look at your console really quickly, I'm going to type out window right here. Remember, this is our window object, which is available to us by default when we are running JavaScript code inside the browser. One or two properties that this window object has is window.innerWidth and window.innerHeight. These two properties are going to give me the entire visible area, or the dimensions of it, that the user can see right now. So it's going to be from that top left corner, just right underneath the back button, all the way down to the bottom right corner of the viewable area. It does not include any space that is taken up by the console. So for example, if I pull the console out and then try to get the width again, I now get a width that is much greater than what I had just a moment ago. You can also see the inner height and width if you are using Chrome. As you drag around the console, just look at the top left-hand corner, or excuse me, the top right-hand corner right there. So as I pull over the console, I'll see that the visible area gets smaller and smaller. So we're going to use window.innerHeight and window.innerWidth to figure out exactly how large we want our canvas to be. So to get started, I'm going to go back over to my index.js file. I'm going to find where we set up height and width right here, and we will pull those values from the window object. So I'll say window.innerWidth is going to be width, and window.innerHeight is going to be height. Now, if I save this file right now and go back over and refresh, I will still see the maze appear, and it's going to take up the full space available to us. If I close my console now and then refresh again, I'll see that it really does take up the entire browser window. However, because of our maze logic, which assumes we always have equal dimensions for the height and the width, well, the entire maze doesn't actually show up correctly. The ball is shown correctly, and our square over here is showing correctly, but the actual walls are not really placed in the appropriate locations. So it's clear that we're still going to have to do a little bit more work to figure out how to get this thing to work correctly. So pause right here. We're going to come back to the next video and discuss the big refactor that we're going to do to a couple of different variables inside of here to get everything else working the way we expect. All right, let's get to it. We're going to start to discuss some of the different variables we need to change inside of here to get our map to display correctly. So, quick diagram. So this is the kind of maze that we want to allow the user to have now. I want to not only allow the entire canvas to be rectangular, but I want the number of cells in the horizontal and vertical direction to be able to vary as well. So we're going to introduce two new variables that are going to replace the single cells variable that we have right now. Remember, cells right now tells us the number of cells that we want to have both in the horizontal and vertical direction. But now I want to be able to have a variable number in the horizontal and vertical instead. So we're going to introduce a variable called cells horizontal. In this case, it would be equal to 4 because I want to have 1, 2, 3, 4 cells going from left to right. We're also going to have cells vertical. And in this case, as you would guess, 1, 2, 3. So let's create both those variables right now, and we'll discuss exactly how we're going to actually use them. Okay, so back over here, I'm going to remove the cells variable, and I'm going to create cells horizontal. I'll start it off as 4, and cells vertical, and I'll start that off as 3. The next variable I want to point out to you is unit length right here. Remember, that was supposed to be the length of one side of a given cell, either the height or the width, because they were always identical. Now that we are allowing for a very different number of cells in the horizontal and vertical direction, and the actual screen space allocated to this can be variable as well, we need to calculate the horizontal difference, or distance of a cell, differently from the vertical height of a cell. So we're going to introduce two other variables as well. One will be unit length x, and the other will be unit length y. And as you would guess, That's going to be the x direction, or the width of a cell, and the height of a cell. We can calculate both these by taking advantage of the height and width of the overall canvas and dividing that by the number of cells on the horizontal and the vertical direction. So back over here, I'm going to change the existing unit length to unit length y, and then to calculate that, we're going to take the overall width of our canvas and divide by the number of cells in the horizontal direction. So that is cells horizontal. So I'll say cells horizontal, like so. Then for the unit length in the y direction, I'll create unit length y, and that's going to be the overall height of the canvas divided by cells vertical. And that's pretty much it. Okay, so now that we've established the meaning of these different variables, we're going to start to go around this file and update all the different references we had previously to unit length or cells to either use cells horizontal, vertical, or unit length x or y. That refactor is going to be just a little bit painful, and I want to put all of it into one single video. So pause right here, come back to the next video, and we'll do the entire refactor, hopefully in one single go. In this video, we're going to do a kind of nasty refactor. So we're going to go through our code. We're going to find every time that we had a reference to cells and remove it. We're going to replace it with a reference to cells horizontal or vertical. We're also going to find every location that we had a reference to unit length x, and we will replace it with a reference to unit length x or y. I can tell you right now that the refactor we're about to do is going to be really nasty. It's very likely that we're going to make a mistake somewhere along the way. So I know that this is going to be kind of annoying refactor. The reason that I decided to do this refactor at the end is that understanding all the maze generation stuff is just a lot easier when the height and width of the maze was always identical. And that's what we did from the get-go. It was a lot easier to take that approach and do the refactor later than to break out the separate or different values of cells in the horizontal and vertical direction from the get-go. That would have been a lot more challenging right away. So I apologize for this video in advance. I'm going to tell you right now, but nonetheless, we got to get it done. So let's get to it. One more time, we're going to go around, find every reference to cells and replace it with one of these two variables. Find every reference to unit length and replace it with one of those two. Okay, let's start. So I'm going to first take a look at the walls array right here. Walls does not have any references to cells or unit length, so no changes required. I'll then take a look at maze generation. Nothing inside of shuffle has any reference to those variables, so no problem. And we get to the first place that we need to start to do a refactor. So where we create grid, verticals, and horizontals. Let me give you a quick overview of why these things need to change now. So here's a demonstration or a maze that we eventually want to have put together. So in this case, we have 4 columns and 3 rows. So let's think about the grid array that we would create to represent this maze. The grid would have basically the same structure as the maze that we're looking at. So it would have 3 rows, and inside of each of those rows, there would be 4 elements, 1 for each column. So they would all start off as false. So like false, false, false. So overall, the grid, the outer array, is length 3. The inner array is length 4. So we need to update the values that we're passing in here to accommodate for that. So the outer array that we are creating right there, that is going to have the number of rows. And our number of rows, if we go all the way back up the top, is cells vertical. So cells vertical is the number of rows that we have. So I'm going to update array cells, the first call right there, to cells vertical. And then the second one will be cells horizontal. Because remember, the inner map, or excuse me, the inner array right here called we have inside the map statement is building out each inner row. And that's going to be the number of columns we have, which is tracked by the cells horizontal variable. Now we can update the 2 other arrays that we generate in an identical fashion. The outer array will be cells vertical. And down here on horizontal, the outer arrays will be cells vertical minus 1. Then on verticals, on the inner array, instead of cells, we'll have cells horizontal. And on this one right here, inside of the horizontals, we will have cells horizontal. Okay, so that's step one. Next up, we need to find a random start row and a random start column. So rather than having this be multiplied by just our total number of cells, we now no longer have that variable, of course. So we need to calculate either a random number from 0 up to our cells horizontal or 0 to cells vertical, depending upon whether we are trying to get a random row or column. So again, cells vertical corresponds to the number of rows that we have. So I'm going to change the start row right here to cells vertical, and the start column will be some random number times cells horizontal. Okay, next up we'll move to step through cell. Inside of here we have just one reference to, or I guess two right here, one place that we reference the cells variable, and that's where we check to see if we are out of bounds. So for next row right here, we're going to make sure that we are not exceeding the total number of vertical cells we have. So cells vertical. With next column, we're going to make sure we don't exceed the total number of columns we have. That will be cells horizontal. All right, just a little bit more. Fortunately, the next one is going to be really easy and straightforward. So I'm going to go down, down, down to where we iterate through horizontals. So inside of horizontals, we've got a ton of different references to our unit length. So we need to make sure we update each of these to either unit length X or Y. But fortunately, like I said, this is going to be really easy refactor. Remember the ordering of arguments we pass into the rectangle function. The first argument is the center of the rectangle in the X direction. So as you would probably guess, we're going to update unit length, both locations inside that first argument, to unit length X. The second argument is the center point of the rectangle in the Y direction. So again, as you would guess, we're going to now multiply by unit length Y and add in unit length Y. Then the third argument is the length of the rectangle in the X direction, so unit length X. Now take a look at this line right here, or this block of code, and make sure you do not have any references to the plain unit length variable. They should all be either unit length X or Y. Okay, so that's it for horizontals. We'll repeat that same process for the verticals as well. So again, first line will be unit length X and X. Second will be unit length Y and Y. And this time, the fourth argument, which is the height of the rectangle we are creating, that needs to be, of course, the height, so in the vertical direction, so unit length Y. Okay, just a little bit more. I know I said this was a nasty refactor, but we're almost done with it. So for the goal right here, we are multiplying by the unit length. Again, we've got the same ordering of arguments. So the first and third arguments need to take a look at the unit length in the X direction. So here's the first argument should go to X. Third argument should go to X. And then the second and fourth arguments are concerned with the Y direction. So we'll do unit length Y and Y. So unit length X, Y, then X and Y. All right, last little bit. Here's our ball right here. So we've got three references to the unit length. Remember, the first and second are the X and Y center points of the ball. So we're going to change the first to X, the second to Y, and then the third argument right here is going to be the radius of the ball. So for the radius of the ball, we might have a very different length in the X direction and the Y direction. So we should really take the minimum of those two and use that to decide exactly what the radius should be. So on the line right above, I'm going to declare a new variable called ball radius. This will be math.min of the unit length in the X direction and the unit length in the Y direction. So find whichever of those two is lesser. And then we're going to divide it by 2. And then I'm going to take out the third argument right here and replace it with ball radius. And I just realized I made the same mistake I did before. The ball, we are providing a radius here, so we actually want to do divided by 4 after the math.min. Okay, so that should be it. So now at this point in time, we should be able to do a search on this file for unit length, and if we search around, we should not find any reference to a variable that says just unit length by itself. So as I go around, I should see everywhere unit length X and unit length Y. I should be able to do the same thing for cells as well. I should be able to search for cells and see everywhere either cells horizontal or cells vertical. So once I've done that check, I'll then save the file. I'm going to go back over and refresh, and that should be it. I should now have my maze showing up in a properly scaled fashion, no matter what the dimensions of my window are. If you refresh and you see an error, I can 100% guarantee you that you just made a typo. So at some location, you put in a reference to the wrong variable. Take a look at the error message and take a look at what line it told you that the error occurred on. You can then go to that line inside of your index.js file, and that will tell you exactly where the typo is. Again, if you have an error where you didn't before, no two ways about it. I absolutely positively guarantee you, you have a typo. So just make sure you take a look and figure out where it is. Okay, so again, I know that refactor is painful, but if we close our console and then refresh, we're going to see that we get this nicely scaled, different sized maze. Now we can do some really interesting things. So we can have different number of cells in the horizontal or vertical direction. So for example, I can have 14 cells in the horizontal and just 10 in the vertical. And if I save that, there we go. And now it doesn't appear that the maze is super squished or anything like that because we are allowing for the different number of cells. So now we can play this thing. You don't have to watch me play it, but I'm going to just solve it really quickly. Come on. Yeah, if you don't want to watch, just pause here, move to the next video, but I've almost got it. There we go. Done. All right, well, I'd say that looks pretty good. So the last thing I want to do is just add in a little bit of color to this thing. And I also want to throw a big message on the center of the screen whenever the user wins as well. So last little task in the next video. All right, the last thing I want to take care of inside of our maze is to just add in a little bit of color and also show a nice message to the user whenever they succeed so that they understand that they really did just win at the game. So we're going to take a look at some of the different shapes that we are creating. We're going to make sure that we add on a fill style to them to just color them in. In addition, I'm going to make sure that when I create my render, so here's our options object right here, I'm also going to flip wireframes to false. Remember, that is what's going to make all of our different shapes solid and allow us to apply some colors to them. So I'm going to update wireframes to false. Then we're going to go down and find where we create all of our different shapes. I'm going to leave the walls as essentially whatever random color we get assigned. I don't really care about those. What I really care about is the different walls, the ball, and the goal. So I'm going to go down to where we create our verticals and horizontals. Here's the horizontals for each right here. I'm going to find where I create the wall. I'm going to add in a new property to this options object. And remember, if we want to customize the color, we can add on a render option with a fill style. And we'll specify the color that we want. So I'm going to try out a color of red. Okay, I'll then go down to where we create our verticals. I'll find the wall that we create in there. I'll find the options object. And I'll also put on a render with a fill style of red. And I'll go down to where we create our goal. I'm going to add on a render with a fill style of green. So just make it a nice green that the user can understand, hey, green is good, right? And then finally, I'll find where we create the ball. In the options object, I'll add on a render and a fill style of blue. So blue for the ball. Okay, so let's save this. I will flip back over, refresh, and now we've got some interesting coloring going on. This is definitely a little bit easier to parse visually, a little bit more interesting as well. The only thing I don't quite like about it is that the ball is a very dark blue. So if you wanted to, you could try out some different colors and find one that maybe suits you better. Okay, so that looks good. So now the last thing I want to do is to make sure once a user wins, we show a message on the very center of the screen that says very clearly, hey, you won. So another quick pause, wrap this thing up in just a moment. All right, in this video, we're going to make sure that we show a really big sign on the very center of the screen that tells the user that they won once they actually, well, win. So to do so, I'm going to go back over to my index.html file. Inside of here, we're going to add in a div element with an h1 inside of it. Now, as a quick reminder, hey, I've said it a billion times, this course is all about the JavaScript. So this is mostly all about styling. So we're going to kind of speed through a little bit of styling to make sure that this message shows up in the correct location. So right above my script tag, I'll add a div with a class of winner and hidden. And then inside the div, I'll place an h1 that says you win. Then inside of my style tag right here, I'm going to add in some styling properties to just style that thing. So first selector I'm going to add in is for the hidden class. So I'm going to say that if an element has the hidden class, then I don't want it to be displayed at all. So I'll say display none important to make sure 100% this thing should not show up on the screen. I'm then going to select the H1. I'm going to give it a color of white and a font size of, how about 36 pixels, nice and large. And then finally, to get this thing centered, I'm going to select the winner class. So that's essentially this div right here. And I'm going to add on a couple of different rules to it. So I'm going to say display of flex. I'll add on a justify content, justify dash content of center, and align dash items of center. So that's what it's going to get it to be centered on the screen. I'll give it a position of absolute and a z index of 1 to make sure that it shows up on top of our canvas element. And then finally, I'll give it a height of 100 VH and a width of 100 VW. And that's going to make sure that it stretches out the full height and width of the screen. Okay, so now if we save this, no need to go refresh, because right now if we refresh, we're not going to see anything because we've got the hidden class on there. And remember, the hidden class hides that div and everything inside of it. So now in order to show this message to our user, once they've hit our win condition, we just have to select this element and remove the hidden class. That will get that div and the h1 side of it to be displayed. So for that, I'll go back over to my index.js file. I'm going to go down to the very bottom where we are handling our win condition right now. And then inside of our if statement, I'll add in a selector. So document.query selector. I'm going to select the element with a class of winner. I'll get the class list, and I will remove the class of hidden. All right, I'm going to save both these files. I'll go back over, I'll refresh, so I don't see anything on the screen right away. I'm going to change my maze dimensions so you don't have to sit here and watch me solve this maze forever. So really quickly, I'm going to change to cells horizontal of, 6 and vertical of 4. There we go, nice and easy to solve. So now I can go on over, solve it, and there we go. I see you win. I think that text could be a little bit larger. So what the heck, I'm going to dial up that font size inside of our style tag right here. I'll go to just a, 64 arbitrarily. Save that. Win again. And that's good enough, I'd say. Okay, so that's pretty much it. That is our maze game. The only downside to this thing is that once a user wins, they essentially can't do anything else until they refresh. So one way you could easily fix that is to just add in a button maybe to recall or wrap all the code we wrote together and throw that all into a function. And then once a user wins, maybe show a button that a user can click to build out the entire grid and verticals and all that kind of stuff again. But I'm going to leave that up as an exercise to you. Give me something that you can implement on your own if you want to, because we've definitely spent a pretty good amount of time on this application already. Okay, so I hope you enjoyed this app. I think that it looks pretty interesting, and hey, who doesn't like a good maze to play around with? So let's take a break here and continue on the next video.